Yeah, here we are. Count up to 10 and let's go.
Okay, so welcome everybody for this, which is the first workshop on perceptual and cognitive issues in extended reality. This is obviously not a novel workshop, but it's the first time we can see and hear about this workshop at ISMAR. So I will just start quickly with some opening remarks and then introducing our first speakers. So first, let's talk a bit about PERCxR. Very difficult to pronounce, in fact, because as most of you know, this year workshop is the following of PERCxR, the very well-known workshop on perceptual and cognitive issues in augmented reality. PERCxR is held usually at IEEE VR conference since 2015. So for this, usually PERCxR is an augmented reality workshop in a virtual reality conference. And was held for 6 years now. And for this year, we wanted to make something a bit different because it was held at ISMAR, so at an extended reality conference. So we wanted to move from PERCxR, focusing only on augmented reality, to a more extended workshop on virtual and augmented reality. So that's why we came up with this very difficult to pronounce acronym. To be honest, I usually say PERCxR also because it's too difficult to pronounce this PERCxR. But you can find some pronunciation if you want. So first, I want to thank people who used to and are still helping us to organize this workshop, what we call our senior PERCxR organizers committee. So thanks a lot for them to helping us organizing this workshop, providing advice and help. So thank you to all of them. They also were part of the reviewing committee. So obviously, as every year, several papers were submitted to be presented during this workshop, and they can be agreed to provide reviews and high quality reviews for this paper, this submission. So thank you to them. So if I talk a bit about the reviewing process of this year PERCxR. So after the submission, we came through a review phase where each submission received 2 reviews from our reviewing committee. And after this phase, we went through a discussion phase and selection phase with the other organizer of the workshop. And at the end, 4 papers will be presented this year in the workshop. And then will be published with the ISMAR proceedings. So let's just go through the schedule of this afternoon is here, maybe this morning for some of you. So the big difference this year is that we are starting with a panel discussion. We wanted to add this slightly different part of the workshop to really go across different senses. Usually we focus a lot on vision in PERCxR, but this year we wanted to extend the scope of the workshop. And so the first part of the workshop will be dedicated to this panel. And we'll discuss the key issues in perception and cognition in extended reality across various senses. So I will then present our panelists, but I want to thank them already for agreeing to participate in this panel. So we'll go through vision, touch, hearing, and cognition. So I have 4 panelists during this workshop. So thank you to Sarah Krimriger, Maud Marshall, Raphael Patrick, and Mark Pilgerst for agreeing to participate in this panel. After that, we'll run through the usual paper presentation. So we have 4 very interesting papers this year. So we have the presentation of the 2 first papers, then a small break of half an hour to be able to chat and to discuss using Gathertown. And then we'll go through the 2 next paper. Obviously, I didn't mention it before, but like always, you can ask any question you want using the chat, so the Zoom chat, the Q&A feature also on Zoom, and you can also use the Discord channel of the conference if you want to. And finally, we will conclude this year workshop by keynote done by Professor Edward Swan, who kindly agreed to talk to us about how the social network of knowledge leads to scientific truth. So I think you are, and I guess you are as exciting as I am to go through this this very exciting schedule. So I think we will start with our panel. If we have all of our panelists, let me check. 1, 3. So yeah, will be barely okay. Mark told me that he will be a bit late, so we'll start with introducing our other panelists and then continue the discussion. So let's share this. Okay. So we'll start our panel. I will introduce each of our panelists very quickly, and then they will talk about themselves, obviously, and the key issues they think are really at stake today on perception and cognition in extended reality in their very specific domain. So for this panel, it's my very pleasure to introduce Sarah Krimriger, who is professor of psychology at the University of Utah, Maud Marshall, who is full professor in computer science at Rennes University, Raphael Patrick, who is assistant professor at Virginia Tech, and Mark Pilgerst, professor of human-computer interaction at the University of South Australia. So I will go through each panelist and let them introduce themselves and present some key issues in perception and cognition in XR. Okay, so I think we can start with you, Sarah.
Hi, can you hear me?
Yes, perfect.
Great, okay, thank you. So I'll introduce myself. I'm a professor in the psychology department at the University of Utah, and I co-direct the Visual Perception and Spatial Cognition Lab with Janine Stefanucci, who's also here today as one of the speakers. And I've been doing research on perception and virtual reality for over 20 years and have more recently, over the past 5 years or so, extended questions asked in VR to augmented reality. And in our lab, we take 2 different approaches with XR that are not mutually exclusive. So first, we use XR to study basic mechanisms of space perception and spatial cognition by taking advantage of the abilities in XR environments to provide immersive and realistic experiences, but at the same time control and manipulate the body and the environment in ways that would be difficult or impossible to do in the real world. Second, we ask application questions about XR itself, such as, do people perceive and act in mediated environments as if they were the real world? And if they don't, what are ways that we can get people to change their behavior? So often these basic and applied research questions can be asked in the same experimental paradigms, and they inform each other. So I've listed a few of the key issues in perception and cognition in XR for vision that I've been thinking about, and I'll just give a brief overview, and then I'm happy to talk about all of these, any of these points later. So first, I think that an overarching goal to support XR applications that require perception of scale is what we refer to in our work as perceptual fidelity. This is the likelihood that people will perceive and act in XR as they would as if it was the real world. Often there are biases in the real world as well. So I think it's important to think about perceptual fidelity relative to what people would do with real objects and environments rather than make claims about absolute accuracy. There's a history of work on distance and size perception in VR that's shown underestimation of scale, that people perceive distances and sizes to be smaller than they perceive matched real world environments. But this has changed somewhat in contemporary VR, and the perceptual fidelity of AR is still an open question, I think. So what are the issues that influence perceptual fidelity? There are a number of factors that we think about in our research that are important to consider in terms of why we might not always see consistent findings or claims about perceptual fidelity. And I've listed a few of these on the slide. First, it's important to consider the region of space over which we're testing visual perception. So there are different visual cues available for spaces that are close to the observer in personal space compared to spaces that are farther away, over which actions like walking can be performed. And also these spaces interact with the XR displays that are used, such as considering how restrictions of field of view require different head movements to see close compared to far objects. Second, I think a critical issue is to ask how to measure perception. So it's not a simple question about how best to determine what we actually see or perceive. And so we've recently been using measures of perceived affordances or judgments of action capabilities in an environment to assess the perceptual fidelity of AR objects, but this is just one measure among many that we can discuss. Third, I think an important issue is how to provide feedback about one's visually guided actions towards virtual objects in mixed reality displays when those objects are not physically present. So for example, we're studying how people make decisions about passing through an aperture, but if they try to walk through an AR aperture, the consequences of bumping into walls are very different than if they were to bump into an actual wall. Now, my other issues on the right side of the slide are kind of on the technology side of XR. So I'll just briefly say what we need to consider differences that emerge with displays. So I mentioned field of view already, but also with AR, we face issues with displays outdoors. And also we need to consider differences in the information that's presented through optical see-through versus video see-through displays, as well as head-worn versus tablet or handheld displays. Other challenges that we face with AR displays include graphics realism. So for example, challenges with virtual objects appearing transparent, with how best to create shadows, and addressing the sense that objects appear to be floating when they're intended to be on the ground. And then finally, we face issues with tracking that relate to visual perception. So for example, if we're interested in measuring perceptual fidelity in distance perception, it's critical that virtual objects are placed accurately in the world. And if we're asking users to move and interact with virtual objects, then it's also critical that those objects remain in stable positions as people move. And this challenge, I think, is even greater as we consider farther distances that are necessary for navigation tasks. So I'll end there, and I'm happy to talk about any of these issues during the discussion.
Thank you for this introduction. I feel indeed a lot of different topics and different very interesting elements about this specific field of visual perception. I really love. But now we have to move to our next panelist. Next on the list is Maud Marshall from Rennes University. So yeah, the same thing. You can introduce yourself and the key issues you might face in perception and cognition in your specific field.
Thank you, Etienne. So I am Maud Marshall. I am a full professor in computer science at University of Rennes in France, and I have now been working on 3D interaction, physics-based simulation, and haptics since 15 years from now, with a lot of applications in virtual reality or augmented reality systems. So today I am in charge of the touch part of this panel. So what we could say about touch for beginning with is like contrary to the other sensory modalities, such as vision or auditory modalities, where the stimuli are located to a unique location in the body, like eyes or here. For the sense of touch, it involves the whole body. And so we generally divide the haptic modality in two different categories: the kinesthetic feedback, of what we call also force feedback, involving the joint and muscles, and the tactile feedback, involving all the mechanoreceptors that we have under our skin. And so since from now, I would say 30 years, there have been a lot of mix of systems mixing haptic interfaces with virtual reality systems. And for this interface, we're mostly kinesthetic interfaces. So we can see here at the top left part of the figure, one of these systems. So these systems are generally very expensive, cumbersome, and for most of them confidential, which means like in the laboratory. And now, since I would say, so 5 years, we have seen an explosion of new haptic technologies. So I put some of them on the picture. I will explain the challenge in terms of perception for them. And these new haptic technologies are using mostly tactile feedback and involve the whole body, either at the micro scale, like for instance in the finger, like you can see at the bottom left part of the finger, or also are using at the macro scale the whole body, such as vest, when you can feel haptic feedback in your whole body. And all these new haptic technologies have been, for most of them, combined with virtual environment or augmented reality environment. So we have therefore new perception challenges going on with these new haptic technologies. And the first of these challenges is where we are using the whole body. So it means that when we were using, as I show on the left part of the figure, we were using physics-based models that were quite accurate and were able to compute nice haptic feedback. When you are using this for the whole body, it's almost impossible for now because of the challenging frame rate that we need for haptics, which like 1 kilohertz, instead of having like the one that for vision, which could be a little bit lower. So we need to find clever approaches to design the rendering of the whole body haptic feedback. Second challenges after the whole body is now that we are using wearables to display pressure, stretch, or temperature, such as in the keynote, for instance, that we have seen of Domenico Praticizzo, and it opens novel possibilities. So with this new wearable haptics device, you can have a haptic device on the whole body, so you can wear them and you can also play with them. So for instance, you can see in the middle, the top part, so a palpation scenario that we had used and designed in augmented and virtual reality systems. And in this scenario, so you are putting a new haptic device on your finger and you can modify the properties of the daily life objects that you are manipulating. So for instance, here you have like a soft abdomen and you can modify the stiffness of this just by stretching the finger. So this is very challenging, but in terms of perception also, it opens a lot of different possibilities because we can transform the way we feel as the object of the daily life object that we can use. We can also use and combine not only tactile feedback, we can use also kinesthetic feedback. So it's like the type of device that we have seen since some years as the ones that, for instance, we did. Here we have an example in the middle still, but in the bottom part, you have like what we call the Ritavix, and this is what we call also an encounter type haptic device. So the ball will reach the hand only when you are manipulating an object in the virtual or augmented reality environment. And in addition, you have also tactile sensation that are incorporated in the ball. So this is a challenging in terms of perception because you have different types of stimuli in terms of haptic and you need to synchronize them such as what you are manipulating or what you are exploring in the virtual environment, need to be synchronized with what you are generating in terms of stimuli. And last, this is the last column of my figures. The last challenges among the three is the synchronization with the other sensory modalities. So I guess this will be what we will discuss after our presentation, how we could synchronize the haptic modality with the other sensory modality. So in the context of XR, for instance, in virtual or augmented reality system, this is crucial for the perception and to keep the sense of presence. So it means that you cannot have like something that is not synchronized between the haptic modality and the visual modality or the auditory modality. So it means that you should find the algorithm for providing this synchronization, but also you can play with this algorithm. So for instance, in this 3 example, where we were using like some homemade haptic device to provide haptic feedback, you can play with the visual modality to modify the perception of the haptic sensations that you can have. So for instance, you have the example of a trumpet where we put some passive haptic device on the hand, and just with the visual modality, you can modify the position of the finger, and then you have the sensation of stiffness that will be modified between the different pistons of your trumpet. You have also the example, like just below the trumpet example of the elastic arm, when you have like a very simple haptic device, but you can combine this with an interaction technique, and then you can explore or manipulate objects just by using this haptic feedback that would provide you sensation of when you reach or not the object. And finally, also there's this new haptic device when you don't have this issue with occlusion, especially for an augmented reality system. This is, for example, the case for a middle haptic device, like the ultrasound device at the bottom right part of the figure, where you can also play with the sensation. For instance, in this example, what we did is to modify the stiffness that you could feel with these ultrasound sensations just by modifying the visual effects that you have. So this is some example of what we could do with a haptic device with 3 main challenges: how we could handle the whole body, how we could synchronize these different types of stimuli, and also how we could synchronize between the other sensory modalities. So I guess we could discuss this afterwards, after the presentation.
Thank you very much for this introduction. Indeed, I think we have a lot to discuss about this synchronization between senses, but we continue to speak about that after the presentation of our next speaker, with Raphaël Patrick from Virginia Tech, and we will be presenting the key issues in perception and cognition in hearing.
Okay, good morning, everyone. So I'm an assistant professor, relatively new in my career, so still don't have any seasoning on, but getting there. I did my background in human factor psychology, so I'm grounded in the psychology domain, and then spread from that system engineering into industrial and system engineering, concentrating in human computer systems. I'm also the director of the Human Impact Lab, where we're really looking at the effect of the human on technology and technology on the human, which is exactly what everyone in this field is doing. So my area is really looking at the audio components. I just boiled it down to kind of 3 main issues, and there's a lot to talk about in each one of these issues, but we're kind of just talking about the general. So just looking at the individual and as a whole. So we just consider this as hearing sensitivity. So just doing this is we understand that all the senses decay over time. Hearing is one of those senses that can be greatly affected instantaneously just because of our environment and the things that we're going through in the daily life. So having a good understanding of what individual or user's hearing sensitivity at the moment of time is very important. So how to actually measure that. And I think our first one was looking at vision and tactile, like how do we actually measure these things appropriately? So one of the issues with looking at hearing sensitivity is what are the scales in which we are measuring the individual and under the conditions that we're doing it. In my lab, in my field, we do a lot of baselining, making sure we're really understanding the core understanding of hearing just at the frequency domain. One thing we're really looking at now and really debating is traditionally you measure sound in decibel hearing levels. And hearing levels is traditionally an average across the population. And that population is usually derived from younger populations, so younger than 17 before your hearing starts to deteriorate. So with that, that means as we get older and different populations are using it, there's kind of a mismatch when it comes to the general hearing levels that we're seeing in references compared to the actual perception that's being experienced by the user. So we're really looking more towards presenting signals in what's called sensational levels, which is really the adjustment to the individual based on the decay of their own experiences. So one of the aspects of doing this and how we're presenting these signals, it doesn't really matter what signals we're presenting. We can always talk about those when it comes to soundification and what those signals are going to actually present, what type of information they're going to present. But we understand, and we're looking at research in this case, where we really know the audio is usually attached to some visuals, right? And we said that from the visual perspective. So we're really looking at how do we kind of move those things apart and what are the effects on that. But that's usually just focusing on how the person hears. So understanding just the basic level of their hearing and then how we can proceed from that. So actually presenting signals at an acceptable listening level or a required listening level, depending on the person's acuity. The second side I really want to discuss is really looking at multimodal perception. Right, we're talking about multimodal senses here, so all going through the array of senses. But within the hearing sense, there's essentially two modes of perception. Right, we can hear using air conduction or sounds permeating in the environment, pushing sound pressures, or we can actually do an internal process, which is really looking at bone conduction hearing. So typically we don't hear ourselves, or we typically hear ourselves in bone conduction in everyday kind of like listening. So if you hear yourself and you hear yourself in a recording, the reason the recording sounds a little bit different and strange to you or alien to you is because you're hearing that from an air conduction perspective. When we hear ourselves, we're usually hear our internal vibrations. So we're really hearing the bone conduction side of ourselves while everybody else in the environment is hearing the air conduction version of ourselves. So when it comes to presenting the opposite portion of that is presenting these signals. There are pros and cons of using one versus the other, but my philosophy is we're going to have to combine both of these modes to make sure that perception in the audio domain is ideal. And shortly, what I'll briefly say on that is from the air conduction side, it's easier to perceive because it really dominates the environment. So it basically masks out other signals as long as it's at the right intensity. However, it does create this occlusion of the environment. So we lose acoustical situational awareness in some positions, right? So we're unable to hear what's going on around us. And especially if we're looking at AR or VR in this case, but AR is a little bit easier because you can still see your environment. But if you're blocked off visually and you are also blocked off acoustically, you're really kind of absent to your environment. So that's the pros and cons of the AR side. On the BC side, it's the quite opposite. You're able to leave your ears open, so the unoccluded effect, which allows you to really perceive what's going on in your environment to actually allow interaction better. So if we're looking at AR, bone conduction may be the better route to go because it allows you to still interact with elements in the environment and actually have acoustic elements in the environment present and actually merge with the sounds that we were presented as stimuli. So my kind of philosophy on that side is we're going to have to move towards these devices that are not kind of like dividing one of the modes, all right, or taking advantage of either or. It's really kind of switching on and off the modes depending on what the situation really is and how we should be perceiving our acoustic environment. And the last one is what we're alluding to is the environmental characteristics. We've seen in other places throughout the conferences that we're talking about technologies that are looking at how sounds are moving through particular spaces. So one of the major issues is how to observe sounds or replicate sounds when there's obstructions. Right, so there's technology out there. I put some links, but there's some technologies out there that are being developed that really looking at how to replicate this, how to do this, how to generate this, and actually have realistic sounds and the motion of sounds replicating in the real environment. But the issue is going to be is how realistic is that? Right. So is it true? So doing the real human testing so we can create these signals, but actually go into the human environment or go into the realistic environment and test these things and see if the sounds are permeating that way. And we're actually perceiving them correctly. So that's really going to be the issue is combining these things together is how are we making sure that the signals are presented at a level that the user is able to actually intelligibly interpret what is being presented to them. Then the multimodal version of that is merging these sounds together, regardless of what mode they're coming in and understanding your situation. And then ultimately, what environment are you presenting these signals in so that you have the best perception and the understanding of your situation. Thank you.
Thank you for this very interesting presentation. I think we have still a lot to discuss together, and with that, I will introduce our last speaker, our last panelist, I guess, Yes, Mark is we joined us. So Mark, I'll let you. You're from the University of South Australia, and you will in this panel introduce ourselves the key issues in perception and cognition, specifically focusing on cognition.
Great, thanks so much. It's so great to be here. So as NTN said, I'm from University of South Australia. I also direct the Empathic Computing Lab, and we try and develop systems that create understanding and connection between people. And an important part of that is cognitive load. And in the AR, VR, XR space, in my opinion, there's several aspects of cognitive load that I think are really important. The first is being able to measure cognitive load. And at the top of those pictures here, you can see a number of new head-mount display devices. And what we're seeing now is, traditionally people would measure cognitive load by using subjective measures and surveys. But what we're seeing now is some new head-mounted displays becoming available that have EEG electrodes embedded in them, or heart rate measurement, or eye gaze tool sensors embedded in them. And so these different devices means that we can now start measuring cognitive load from within AR and VR applications, which is a really important trend. Second important thing is designing for cognitive load. So there's really several elements of that, at least several. One is designing for humans working or long-term memory, so and being able to support that. The second is being able to better support decision-making process. And you can see on the right-hand side there the picture of the Google Maps AR interface. And in this case, they're using augmented reality to help us better navigate. And they show both a first-person view that shows virtual tags in the real world, as well as a map or third-person view showing your top-down view onto that map. So by combining both egocentric and exocentric views, it provides a better support for your decision-making process. Another element I think is really important is looking at cognitive load in collaborative situations, and that's what we do a lot of in my lab, and particularly looking at brain synchronization. So when you've got several people performing the same activity or engaged in the same task, sometimes their mental brain activity becomes in sync. The electrical signals of the brain become in phase, and when that happens, people report that they feel more connected or they're working together much better. And so that's an example of a distributed cognition process where you've got several people working together and you're trying to measure the cognitive load or the mental activity of everybody at once. And it turns out that hasn't been very well studied in AR and VR yet. So we're doing some work in that space, and it's a very exciting space to look into. And then the final area, which is really exciting as well, is, once you can measure cognitive load, you can design for it. You can also look at new types of applications. And so, for example, in our lab, we've been doing some work on building learning environments that automatically adapt to people's cognitive load. So, for example, if the learner is finding the learning experience very easy and they have a very low cognitive load, then we may want to increase the difficulty of the learning experience. If it's too hard, they may feel overwhelmed and want to give up. And then what we can do is we can reduce the complexity of the learning experience so the cognitive load gets into the peak region. So I think with new types of AR and VR displays that can measure people's cognitive load in near real time, you're going to start seeing these new applications now that enable us to build adaptive interfaces or build intelligent user interfaces. For example, virtual characters in AR and VR that will be able to respond to our cognitive load and emotional state. So those are some of the important elements, I think, in the area of cognition, and hopefully we'll be able to discuss some of those in the Q&A session now, and also throughout the rest of the workshop this afternoon. So thank you very much for the time.
Thank you, everyone, for your introduction. So we'll now start our discussion, and so I have to recall for the public that you can use the Q&A section of Zoom if you want to ask questions to our panel. Otherwise, I have a lot of questions to ask. So, but if you want to share your thoughts and your questions about those perceptual issues, please use the Q&A feature of Zoom. So first, thank you, everyone. And I would like to, I'm not sure if we can see all of you. on the screen right now, but I think if you start talking, we can see you. So it's okay. My first question, I have a very generic and I would say usual question for all of you, which is, what do you think is the biggest, the most important thing about perception and or cognition, the most important problem that has to be solved in order to have to solve, in fact, the extended reality as a whole, in order to fix extended reality to be able for this new technology to succeed. For you, what is the most important issue, the most important problem for perception and cognition? I don't know if some of you want to start, but.
I guess I'll be brave and step out. Honestly, I think this might just be me as a psychologist, but I think it's understanding the person, right? We can talk about the technology and what type of technology is going to be used and what the environment, all these other aspects. But to me, I think all of the panelists kind of touched on it in some ways. It's really understanding how to measure the person accurately, right? Whatever sense we're dealing with, it doesn't matter. Psychophysics is all the same, right? It's just a matter of how do we do it and make sure we're really accounting for the individual differences in the person, and then actually understanding those things and applying them appropriately to the technology and the field of their task.
I can follow up with that. That's a great answer, Raphael. I think in the last couple of decades, to a large extent, the AR and VR field has been driven by engineers and people who are building technology. But what I'm hoping to see now, and what I think is happening, is that we're now getting to understand that actually an AR and VR experience is really a perceptual experience and to some extent a neurological experience. So if you want to be able to build really great XR experiences, you really do need, like Raphael said, you need to be able to understand the cognitive and perceptual underpinnings of that. For example, a simple example, if you want to be able to make a AR content that appears part of the real world, then you need to be able to provide some of the depth cues and perceptual cues that we normally have from real objects. And for a long time, people weren't doing that. So you had virtual objects that would pop out of the real world and wouldn't really look as part of it. But now people are producing pretty amazing AR content that casts shadows and can be lit from objects in the real world and perceptually, to a large extent, indistinguishable. So I really think, as Raphael said, that it's really about understanding the person and getting understanding also of the cognitive and neurological processes that create the illusion of AR and VR.
I'll just say that I totally agree with both of those responses. I also, coming from psychology, feel like we need to, focus on the person, and I guess I would say again, kind of, as I introduced in my presentation, that we know we can use AR to augment the real world, but it's not going to be as effective if people don't treat the augmentation as if it were the real world in some way, right? So we need to kind of do these, as Raphael said, these measurements to kind of assess whether people are treating this mediated environment in a similar way as the real world. And we know it's not the same, right? But looking at these, whether the processes are the same, I think is key. So really focusing on that human perception and behavior is going to take us farther.
Yes, and to finish, I totally also agree with all your answers. And to finish, also, I think also, one point is like, if we are using all the sensory modalities, sometimes it's quite interesting to see how cross-modal interaction we could have, and we could play also with the other modalities, like for instance, I would say haptic or audio, to change or perceive differently, because we know that vision is predominant when we have like augmented or virtual reality systems. And this is somehow very different depending on the people. So I guess this is also quite a nice challenge to understand how we could mix these modalities all together.
And we have a great question in the Q&A from Rick Carlos to continue, because you say that all of you agrees that it depends on people, it depends on the mix between all the perceptual channels. Sorry, and Rick is asking, do you think that how do the perceptual factors affect cognition and possibly vice versa? Specifically, can you speculate on the effects that matches among different perceptual channels might have on cognition? So how different differences in perceptual channels can affect cognition?
That's a great question. I can talk a little bit about that. So there's a couple of ways. First of all, if you have a mismatch between the perceptual cues that you're providing somebody, that could increase cognitive load while people try to make sense of it, and also could produce stress on the person. So for example, with many AR displays, they have a fixed focal length, maybe 1 meter, 1.5 meter, or 2 meter. And so if you want to show virtual content that is appearing on your hand, as you move your hand close to your face, it becomes impossible now to keep your hand in focus while the AR content is in focus. And so then you have to have a switching between focusing either on the content or on the hand and going back and forward and trying to perceptually make sense of that. And so that can then increase the cognitive load, because you have to swap focal lengths on the eye. That could also lead to accommodation and divergence problems, and then poor performance in a task you're trying to achieve at the time. So that's one example of how a mismatch in perception between the AR content and the real world content can lead to other challenges when you start performing tasks in those settings.
I could add on that. I think Maud kind of like led us into that. I agree with what Mark says. If we just go back to pure psychophysics, right, and we know that there's senses, we'll stop at 5, right? There's other ones that Mark alludes to, right? Shared consciousness and things like that. But it's really interesting to understand what happens when we start to pull these things apart, right? Because naturally, as a human being, we take in all the information at one time from all the senses, especially tactile, right? We feel it all over our bodies, and we kind of like, indirectly kind of understand what is going on with our environment because of these things, right? In the AR context, it's all virtual, it's all recreated, but it's still some situation that is happening. It's really interesting, I think, to really kind of parse these things apart, right? Pulling away the visuals from the audios, right? What is it like when an audio that should be attached to a visual object is moved away from that object, right? How far? What are our affordances? How far can we move these things? Having some idea of that, right? Some just noticeable differences between those things may give us a way to kind of reduce the loads. Right, we can pull things away from each other just a little bit, right? And that might reduce the cognitive load, or making sure that things are within the tolerance to make sure that you're not taxing the brain to then converge things together that are not perceived to be together. So having some understanding of the relationship between one sense and the other, and how they all bring together and share or create a mental model for us would be interesting to give us some tolerances.
And do you think that such a meta model is achievable?
At some point in time, right? We hope that we should have, right? So the designer is creating something that they want the person to experience, right? If we say a video game, right? You want them to experience this game in this way, right? If it's not perceived that way, our whole purpose may be different, right? Playing the game and engaging with this activity can be completely different than what the designer wanted us to be, right? And those could be, like Mark said, could be directly linked to the elements in the environment, how we're positioning them, right? And how we're actually presenting them to the user. So it could be really interesting to see what happens if we kind of go over our limits, right? Or stay within our boundaries. But we would need to know that as scientists and engineers to craft that into our system, to do it on purpose for experimentation, or making sure we abide by these rules to make sure we have the right situations.
I don't know if someone will want to elaborate on that, or if we go to the, because we have.
I just would like to answer to the question also about haptic, maybe because there was a specific end of the question was for haptic. We now know that we have differences, for instance, when you are delivering haptic forces in AR versus VR, so meaning that you don't have the same properties. So we know that AR and VR, we have like two different perception. So we have some studies that are demonstrating that. So I guess this would be very interesting also to see and to understand in AR versus VR how we could use haptics in terms of this subtractive like AR. This is something that is mostly unexplored for the moment, but I am sure that this is two different ways of handling things, like if we have like complete virtual environment compared to a AR environment.
Yes, these issues of complementing and subtracting perceptual channels also, it's really interesting. I was wondering if you think that the sorry, I lost my what is the most important difference between AR and VR? Because today we're supposed to talk about extended reality, but in fact we didn't precise if we want to go for AR or VR. And I think that for some senses, there is big differences between AR and VR. Technologies are different and the goals are also different. Do you think that what is the biggest difference between AR and VR in your point of view?
Well, I think one thing is that with VR, the goal, of course, is to replace the real reality with computer-generated images, and because of that, it's actually very difficult to create reproduce all of those sensations. So you may be able to see the graphics, maybe photorealistic, but you can't get the haptics, or you don't have some of the other cues represented. With augmented reality, of course, you're layering on top of the real world. So in many ways, augmented reality is easier, or is perceptually easier to have a consistent perceptual field, because when you look at a real block, for example, and you've got a augmented content on top of it, you can easily reach out and grab the block and feel it and touch it, everything like that. So you don't get simulated sickness in augmented reality, where you get the visual vestibular mismatch as you do in virtual reality. So in many ways, I think in virtual reality, you have a much greater chance of having that perceptual mismatch than what you might get in augmented reality. So it's one difference, I think.
I would say from the vision perspective, augmented reality is really exciting, right? Because we have the real world, and that's the big difference between AR and VR, in that in totally complete VR, the real world cues are not available, and we know that the information in the real world is very important in the context of perceiving the scale of spaces. And so I've been really excited to work with AR, but then we face these different challenges, that in VR you can actually kind of have this overall kind of realism, in a sense that we don't have to worry as much about people kind of having distortions and perceiving the graphics as not consistent with the real world. In VR, you kind of have this total consistency, right? It's the same context. So and we also, with current AR devices, such as like the HoloLens, it's not ideal, right? Because we have the real world and we have the full field of view of the real world, but we then just have this like small piece of graphics that's like superimposed onto it. So I think looking ahead, if we have improvements in devices that can give us kind of more full field of view for AR, I think that will also possibly help.
I could touch on that from the audio, and I'll make it quick. I think from the audio perspective is, you're expecting, if you're looking in AR, right, you're expecting to look around your environment, see that object emitting the sounds. Like, you're looking for what it is in the real world. In the virtual reality, it's kind of, you're expecting it to be artificial, it's artificial. So you're kind of just saying, okay, what should it be attached to in some ways? So I think from the audio perspective, there's kind of like a search for like, what is it, right? Like, where is it coming from? And does it really match that thing? And does it really sound like that and feel like that in the real world? So it's the difference of kind of that perception of presence.
Yeah, we'll finish with haptics, and I would say also we can play. I would say use the word play in VR with the perception, because as we have this mismatch, and we can play with them to enrich the virtual environment with a different type of perception, because we can do what we want with the object somehow. While in augmented reality, I mean, as you have the real world somehow, I mean, you have some more constraints, but in parallel, so I mean, this is very specific to haptic, because for haptic, you need haptic devices. And it means that in augmented reality, you see these haptic devices, while in VR, you don't see them. For instance, if you have them on your hand, so you can play with the hand, that would be an avatar without any issue, while in augmented reality, you can see the haptic devices. So you need to somehow find some solutions, even if you have these haptic devices that are visible, to play with the perception if you want to add haptic content in addition to the real world.
I want to add also that one interesting element of augmented reality is being able to mediate your view of the real world and actually remove elements of the real world. So which you can't really do with virtual reality. So for example, you could imagine having a physical ad blocker. So when you're wearing your augmented reality glasses, whenever you see a billboard in the real world, it replaces the advertising with something else, a picture of flowers or something. And so you're actually, so with augmented reality, you can have enhancing the real world, but also you can look at trying to remove elements of the real world and change your perception in that way as well, which is also a very interesting and exciting difference from what you get with VR.
And yeah, there's two things really interesting here. And first, I will speak about the devices, because for haptic, you said that the haptic devices are always, you can always see those devices. Sarah, you also mentioned the issues and vision for these devices. And then do you think that all the senses will be someday stimulated the proper way? I want to say that by that maybe we'll never be able to have some haptic device which is unnoticeable. Maybe we won't be able to have a vision device, a display device, which is unnoticeable. And do you think it's an issue for the use of augmented reality? How can we fix that, by the way?
I think that's a really interesting question. And it would be great to get opinions of the people on the panel, because in my opinion, with some of the new head-mount displays like the Vaio VR display, this one in the center of the display can basically have human eye resolution graphics, and connected up to the right graphics card, you can pretty much have photorealistic human eye resolution graphics in the display. So we're kind of there now with realistic graphics, but it'll be interesting to see what other people think about how far behind we are in terms of audio and the haptics. I remember going to SIGGRAPH 20 years ago, and they made a big deal about, it was the first SIGGRAPH where they had a graphics card that could draw 1 million triangles a second. And in 20 years since that time, we've got that, cards that can do billions of triangles a second, and our mobile phones are more powerful than that. So I'm not quite sure how long it will be before we get to the point where we can have imperceptible differences between spatial audio and audio in the real world, or between haptics or tactile sensations, or even our sense of smell and other sensations. I think we're almost there with graphics, but I don't know if it's 20 more years before we have haptics, or 50 years, or how long it'll be before those other sensations are also feeling the same as in the real world.
Yeah, maybe I will start with haptics. Maybe Raphael will do after the audio. I think in terms of haptics, as I said in the introduction, I guess we have seen this last year, like an increasing number of new haptic technologies that are now wearables on the whole body, and even you have like middle haptic device when you don't have anything in your hand, because you have like an ultrasound device, for instance, and you can feel. And for instance, you don't see anymore the haptic device in your closed environment. And I think we are doing so many improvements in terms of haptic hardware that now we have like we're able to manage and to generate like a lot of different stimuli. But then now we need to find somehow like the algorithm to mix them in order to convince or to provide something that is convincing when you are like in augmented or virtual environments. And that's maybe the next step. And I guess if we want to do like a parallel with graphics, when we had the hardware and then we worked on the algorithm, then maybe we are like at that step when we are doing haptics now. But with like this new improvement on hardware this last years, I am quite convinced that we will do a lot of progress and we will find some solutions. But still, we will also have like we observe now that there's cognitive issues. You cannot put the haptic stimuli in the hand of a user without any cognitive issues at the hand, because if you are putting too many stimuli, this is somehow unuseful. So I guess this is the main challenges we'll have with this cognition issues also.
Yeah, agreed. And from the audio perspective, I think technology is really moving forward. So there's a lot of technology out there. Audio is, in some cases, considered the second sense, right? And there's a lot, right? You can isolate yourself. But I think what the issues we're seeing with the audio perspective is what's driving the decisions to put audio components into things. Right? I think in some cases, the gaming industry is really big when it comes to working spatial audio, right? It's because it's the experience. If you're looking at gaming engines, they use audio as a way to navigate the user in open world environments, right? So audio is really used to an effect, and spatial audio is really developed in that space using Unity and the other softwares that we have and the other techniques that we have. But what we're seeing, and especially Google Glass, right? If you go back way back when to the first kind of groups of technology that came out, they tried to incorporate bone conduction, right? So if we talk about this other mode of hearing, right, there's a value because your ears are open. However, there's not a very grounded understanding in how to apply those things because there's not the conversions between air conduction and bone conduction are still incomplete. Right. So that is the big thing. And that was one of the things I was working towards in my lab or continue to work towards. But we had to create the methodology to even test it. Right. And then once we've created the methodology, now we have to get the users to actually create it. And it takes a large sample to actually get something like that as equal loudness contours. So I think from the audio perspective is audio is there. Right. There's the capacities there that we can do it. It's just how do we apply it and how are we applying it correctly? And then the last factor is it's different for every single person. Right, like other ones, we can adjust it for certain things, but audio is very, very finicky in some ways, right? If you're off by a few decibels, then the entire experience will not be spatialized anymore. It will just be lopsided in one direction.
Thank you. Maybe Sarah, you want to elaborate something about some things on this subject, or we can run through our last question because we're running out of time.
Sure,
so.
We can go on. Yeah, I think Mark already communicated, right? Like in vision, maybe we're kind of closer there in terms of the hardware and technology that's there. But I would just also add that, I mean, we have the Vario. It's amazing. Like I just feel like this is a like amazing XR experience. But we still have to then consider that, you know, somebody's wearing a heavy helmet on their head and they're still exactly what Mark has been saying. There's these cognitive aspects that we just can't get rid of unless we're, you know, really just kind of directly stimulating the retina or something to get these experiences. So I think it's really important to kind of have this discussion of the interaction between the perception and the cognition.
Thank you. And we have a very interesting question from Ferran Argel again. In the chat is asking that for now, our experiments about perception in general are very short, and we're just measuring very specific things. And we experience some distorted perception. But when users be habituated at this distorted reality, would those perceptual issues fade away because of this adaptation? Do you think that we can achieve to have some natural or somewhat natural interaction between users and MR devices thanks to this adaptation in longer exposure?
There's a famous study that I think many of you may be aware of, where I can't remember the psychology that did it, but the psychologists did it, but they wore a special pair of glasses that inverted the world upside down. And you know, it took about, I think it was a day or a day and a half, and then they could then start perceiving the world as normal, even though these glasses were inverting the world. And then when they took the glasses off again, it took a day and a half or so to swap back. So the human brain is really, really plastic. And so that means that, as in the comment there could be issues with adaptation over time. And it might be that we learn to adapt to the limitations of the technology that we have. And then when we get newer technology or take the technology off our heads or whatever else, and we have to have another period of adaptation coming back the other way. A crude example of that, I guess, is with our mobile phones and maps. And you know, now, because most people have mobile phones with a map on it, you might be getting a generation of younger people who really can't sense direction from their surroundings. They always have to rely on their mobile that has they've grown up with through their life. So it's true that you know, if you could imagine a smart glass AR system that lets us enhances, we may adapt our lives to it over long periods of time.
I agree with that, especially from the audio perspective. We've seen a lot of younger kids growing up constantly attached with AirPods, right? They're always listening to music. It's becoming a normal thing for them. So the question of adoption is really interesting. I think from all of the senses, Mark starting off with cognition, right, where it ultimately goes. But I think the senses themselves, they may get worn out over time, right? So decay rates may increase, right? So my argument may be like, hey, now we have to check baselines even more often because, you know, you're using these things for prolonged periods of time. In the audio domain, it's always about the intensity in which you are listening to the stimuli, right, and the intensity over this duration, right? So you start to reduce and you increase your decay rate because you're listening, your exposure rates are higher. So I think that, yeah, adaptation is great, but then there might be a negative effect of that when it comes to listening or, you know, staring at the screens too long. We've seen that question over time.
I'm really sorry. I have to jump out to another meeting. I'm supposed to be talking at tutorial, so I'll let you guys go. But thank you so much. It's been great seeing you all.
Thank you, Mark, for joining.
Thank you.
Some more on Sarah, if you want to, yeah.
Yeah, I would say we have the same issues for haptics because we said at the beginning of the panel that we will have a difference between users, but we also have a difference in time. I mean, even for each user, there is like an adaptation. So as the haptics community, I've studied for a long time this like this sensitivity that will decrease or increase depending on the time for each user. So I guess, yes, this is the question. If we want to use this haptic signals for a long time, of course, we'll not have exactly the same type of perceptions that if we're using this for a small time over for a short period.
I guess, Sarah, you have the closing words for this.
Okay, well, I just want to say, I think that's I love this question about adaptation because we know that people will adapt when they're in these virtual or mixed reality environments. And we see that even over just a few minutes of walking around in a virtual world, people show this kind of recalibration or adjustment to their experience of how the visual world changes with their actions. And you can make those same parallels, I think, to all the senses. And so so we don't know that much about if you were to have somebody in VR or AR mixed reality for extended periods of time, but I think we could make some predictions that people would adapt. And then the question is just what would be the consequences when they go back to the real world, right? That we would need to kind of have this other period of adaptation as well.
I think the true question, if I close it real quick, is will we shift dominance? Right. Well, one of the senses, because we're getting it more often, become the primary sense that we're really drawing information from our environment. Will we get that shift? Right. Just because we're constantly exposed to it. Like I think that the tactile sense is one of those that can rise just because we're being overstimulated. Right. It might become the main source of information coming from that space now.
Yes, thank you very much for this very interesting discussion and perspective. Unfortunately, we have to stop because we have to move on for the following of schedule. But anyway, thank you a lot for all this discussion, and we can also continue this discussion during the break with our panelists on all of attendees. And yes, so I will just let the floor to Nayara for introducing the following speakers and paper. And thanks again to our panelists.
So yeah, now we're gonna continue with our schedule. The way that we're gonna work, we're gonna have 4 papers presentations today. And we're gonna have about 10 minutes of presentations and 10 minutes of questions. So I ask if you have questions, you can post them during the presentations here on the chat, or you can also send them on the Discord channel. So it's up to you. You can post them during the presentation. Our first paper that we have today is going to be presented by Janine Stefanucci from the University of Utah. The title is Comparing Distance Judgments in Real and Augmented Reality. So I'm going to share here.
Hi, I'm Janine Stefanucci, and I'm going to talk to you today about our work comparing distance judgments in real and augmented reality. This is work done in collaboration with my colleague at the University of Utah, Sarah Creamer-Gear, and our collaborator, Bobby Bodenheimer at Vanderbilt University. It's sponsored by the Office of Naval Research. So what I want to talk to you about today is focused on a particular research problem that our group has investigated for many years now. It's what we call perceptual fidelity. We define perceptual fidelity as the ability of a mediated environment, be it displayed through augmented or virtual reality, to simulate experiences that are similar to perception in the real world. In the case of augmented reality, such fidelity is important to ensure that any training done in AR will adequately and easily transfer to a real environment if necessary. Perceptual fidelity can also be used to characterize the level of realness of an AR simulation as well. In the current study, we investigated the fidelity of AR in the area of distance perception, specifically egocentric distances, or those from an observer to another object in the environment. Prior work in the real world has shown that egocentric distances are slightly underestimated. And this level of underestimation may be related to measures that are used to assess distance perception. In contrast, egocentric distances in augmented reality have been shown to be overestimated in some experiments, but underestimated in others. This difference in over versus underestimation could be due to the technology used to display the targets. Tablet-based AR, for example, has been shown to be different for perceiving distance when compared to head-mounted devices for AR. And cues available in the environment in which the distances are displayed may also affect judgments. For example, displaying a virtual target outdoors may provide different information for judging distance compared to indoor environments. Another cue for judgments of egocentric distance that's particularly important is stereo vision. Rosales et al. 2019 showed that virtual targets displayed in augmented reality with the HoloLens 1 were perceived less accurately when stereoscopic cues for depth were removed by having participants view those distances with only one eye, or what we call monocularly. However, in their study, they did not compare judgments for virtual targets to real targets, nor did they assess the perceptual fidelity of the AR overall. All judgments were made in AR. So we propose to assess judgments in the real world. However, we believe that to be an appropriate comparison to judgments made in AR, we need to control for the weight of the AR device by having participants wear it even when making real-world judgments. Rosales et al. Did not have participants do this, but this idea is partially motivated by prior work from our group that found that weight and inertia of head-mounted displays for virtual reality can affect distance judgments in the real world. So in the current study, we asked participants to judge egocentric distances to either a target displayed in augmented reality, so virtually, or a target displayed in the real world. To control for the weight of the AR device, we used the HoloLens 1. We had all participants wear the device while making estimates. We also tested whether stereo cues to depth would affect estimates by having participants view the targets both binocularly and monocularly. Based on our prior work, we had two hypotheses. First, we postulated that distances to virtual targets displayed in augmented reality would be underestimated more than real targets displayed in the same environment. Second, we hypothesized that distances would be underestimated when viewed with just one eye or monocularly, and that this reduction in stereo cues to depth would particularly affect the viewing of virtual targets shown in AR. For our experiment, we used the HoloLens 1 to display the virtual target, which was a white virtual cube shown pictured here in our laboratory environment. The real-world target was an analogous white cube that was printed 3D from the model used to create the virtual target. The HoloLens itself is an optical see-through device with a field of view of 34 degrees diagonal, and it weighs about 580 or 579 grams. This weight is important to note, given that other virtual reality devices weigh less than the HoloLens. The Oculus Rift, for example, weighs only 440 grams, and the HTC Vive weighs about 555 grams. So we collected data from 28 participants. Each participant viewed 3 different distances, 3 meters, 4.5 meters, and 6 meters, 3 times each for 2 blocks of trials. The blocks consisted of either monocular viewing of targets or binocular viewing of targets. And the order of viewing condition, binocular or monocular, was counterbalanced across participants. The reality condition was manipulated between participants. 14 participants viewed the virtual targets, both monocularly and binocularly, and then 14 participants viewed the real target. While wearing the HoloLens, it just wasn't powered on. Again, they viewed the real target both monocularly and binocularly. To achieve monocular viewing, all we did was have participants put an eye patch over their non-dominant eye. Participants estimated the distance to the targets by viewing the actual target, closing their eyes, and walking without vision to the apparent location of that previously viewed target. Their walked distance then served as their estimate of the perceived or apparent distance that they had viewed to the target. This measure has been widely used in the distance perception research field, and it's often called blind walking. So as a reminder, our first hypothesis was that virtual targets displayed via AR with the HoloLens would be underestimated more than real targets. Unfortunately, this hypothesis was not supported by our analyses. What you see here in these graphs is the actual distance displayed on the x-axis, and then the estimated as blind walked distance displayed on the y-axis. The left graph is monocular viewing or one-eye viewing of the targets, and the right graph is binocular viewing for both conditions, AR and the real world. This dotted black line represents perfect accuracy. So what you see in both graphs is that estimates are below accurate. So we found general underestimation for both reality conditions across all distances. And this underestimation did not differ on average for augmented targets or virtual targets compared to real targets. We did, however, find a 3-way interaction with viewing condition, distance, and reality condition. Distance was underestimated for both the AR and real-world groups, but this underestimation actually differed across the viewing conditions, monocular and binocular, for each group. So to further analyze this interaction, we ran a separate set of ANOVAs for the monocular and binocular viewing conditions. For the binocular condition, the analysis didn't support a difference between the AR, the blue line, and the real world, the yellow dotted line, conditions in terms of distance perception. However, for the monocular viewing condition, distances were underestimated more at the farther distances, 4.5 and 6 meters in AR compared to when the real targets were viewed. So there was no effective order of viewing condition in this case, but these results partially support our second hypothesis that distances would be underestimated more in AR, and that this would be especially true when those distances were viewed monocularly. So what can we conclude from our findings? Well, our first conclusion is that the perceived egocentric distance to targets displayed in the HoloLens 1 is underestimated in a manner that looks to be similar to what's observed for targets that are shown in reality, in real targets in the real world. We acknowledge that our findings can only speak to distances that range up to 6 meters, or what's often called action space in perceptual psychology. But we also believe that the weight of the HoloLens wasn't a strong contributor here to the underestimation we observed, given it was controlled for in both conditions. Our second conclusion supports the findings of Rosales et al. 2019, which is that stereo cues for distance are important for perceiving depth in AR. And when those stereo cues are removed, greater underestimation of distance can occur. What implications do our findings have then for the field? Well, to return to the motivation for this talk, we believe that the HoloLens 1 seems suitable for use with tasks that require distance estimation in the range we investigated in this experiment. Or put another way, the HoloLens seems to have good perceptual fidelity. And this is useful for thinking about using AR for training and simulation in the future. However, our work obviously raises many questions that we would like to investigate in future work. For example, we want to replicate this experiment using the HoloLens 2 to test whether field of view maybe was a potential factor in the observed underestimation to virtual targets. We also didn't display shadows around the virtual targets, which could have affected the perception of their location, especially when viewed monocularly. Our student Haley Adams is running studies now to examine the effect that shadows may have on distance perception to targets. Finally, we'd like to also examine whether the presence or absence of stereo cues for depth may interact with other distance cues available in AR and in different environments in which virtual targets are displayed. So I just want to thank my collaborators, Sarah Creamer-Gear and Bobby Bodenheimer, our research assistant, Lenny Wright, for collecting these data, and also the Office of Naval Research for sponsoring this work. Thank you for listening, and I'm happy to take questions.
Thank you, Janine. If you can now come online, you can turn on your video. We have some questions for you. So the first question that we have here, do you think the underestimation of distance is due to the method that you use of blind walking method? Do you think if you had to use a different method would make a difference in your results? Janine, you there?
I'm not sure. It sounds like she's not there, but I can answer that if you want. So I think it's a good question about, does the measure influence the level of underestimation? But it's actually the case that in blind walking, we typically see more accurate estimations than verbal reports. So I think in this case, the blind walking is probably not the explanation for the underestimation. But it is important to consider multiple types of measures.
Okay, thank you. I also have another question. I don't know if you can answer it, or
I just would
she's able
say,
to actually turn on the audio.
Janine just commented that she's here but has no way of turning on the camera. So I think she doesn't have the audio either, or the mic.
Oh, let me try. I'm not being able to make her panelist either.
She's listed on the list of panelists. Obviously, I guess because she's showing up on the Zoom.
Yeah, I'm seeing two accounts for her. I think she has the wrong account listed as panelist.
Okay.
Okay.
Sorry, I'm here. I just sorry about that.
So I have another question for you.
Please.
So do you think that interleaving the monocular binocular trials could have any impact on your results? In other words, do you think that switching between monocular and binocular cues might have impacted the results that you found?
Yeah, so if we had randomized whether they got monocular versus binocular trials within a block, I think that could have affected things, because I think once you've seen the cue binocularly or the target binocularly, you have more information. It would be hard to run that way because everyone's wearing the HoloLens. So it would be a lot of like, let's lift up the device, let's put the eye patch on. And so then you'd have to re-register the room in the case of the virtual targets. So that's why we didn't do it that way. But I do think that could have played a role. We didn't find order effects. So we didn't find that people who did binocular or monocular viewing first, it affected their second set of trials. But we only had about 7 people in each order. So I'm not sure that if we hadn't run more people, we wouldn't have seen some effects, or if you had seen it binocularly before, the monocular effect may not have been as strong.
Okay, I see.
Yeah.
And also another question. I'm not familiar with this blind walk method, right? So I was wondering, do you think that maybe people were just underestimating the distance because of the different perceptual how blind walk works? Maybe did you do like I would say a baseline condition? Do you think you would have find a different result to compare one person?
Yeah, that's a great question. So this blind walking has been used in a lot of studies now. So it's a pretty widely used tool for measuring distance perception. One of the things I didn't say in the talk, but is in the paper, is that we always do training with blind walking before participants start so that they're comfortable with the measure and they know how to kind of walk around without vision, and that there's someone in the room to guide them back to the starting location when they're done. And so usually though, in the real world, when you give people just a little bit of training at the beginning of the experiment, they're actually really accurate at walking to targets, and people really find this unbelievable. I do a demonstration of this in my class always, and students are always surprised that they can actually walk to this target without vision with very little training. So I don't think it was necessarily a measure issue. In fact, I think it was more surprising that we got underestimation, given this measure usually shows accuracy in terms of walked distance, or slightly underestimated, but not to the extent that we saw.
So you mentioned that the weight of the device also influenced the distance estimation, right? What other factors you believe that could affect the estimation of distance using AR?
So we definitely are interested, like I said at the end of my talk, in kind of exploring other cues. As you saw in the images in the talk, we had a room that was populated with like chairs around the edges of the walls, but this is very different than when you think about walking in a room with lots of objects in it, right? That's furnished and has other objects that can serve as cues for where the target might be located. So that is a difference, that in a cluttered environment, you could imagine there would be different information for where the target is. Shadows are an obvious factor, and the fact that the augmented targets didn't have a shadow on the ground, the real target obviously did, because it would have cast a shadow in the room, is an interesting question that our student Haley is pursuing. And then also, I think, the indoor-outdoor question is a really interesting one. Indoor rooms provide all of this clutter, and information like the walls as boundaries. We know that matters in terms of estimating distance, whereas if it's outdoors, the cues become a little different. And the AR technology, as we heard about in the panel, also doesn't work as well. And so one of the things we're really interested in pursuing is trying to do some of these distance estimation tasks outdoors with newer AR devices that can handle outdoor lighting.
So yeah, guys, we are running out of time. Thank you very much for the presentation today and answering the questions. And we can meet during the break in 30 minutes, so we can talk more about it and have other questions.
Thanks so much.
Thank you. So we're right on time. Our next paper is from Vanderbilt University and University of Utah. The title is Distance Estimation with Social Distancing, a Mobile Augmented Reality Study. And again, if you guys have any questions, you can post them on Zoom. I'm going to start sharing my screen.
Today, I am going to discuss about the paper called Distance Estimation with Social Distancing, a Mobile Augmented Reality Study. In today's era, we can develop augmented reality applications on various AR head-mounted displays, such as the Microsoft HoloLens or the Z Mini, as well as on our regular mobile devices, such as iPhones, iPads, or various Android devices, because of their adequate hardware capability to run AR apps. However, if you go through the AR literature in general, you will find that most of the studies have been conducted using AR HMDs. In our study, we mainly focused on the mobile AR displays, and we ran a distance estimation study using these devices. Here comes the first question, and that is, what are the motivations of our study? Some of the previous distance estimation researches conducted in mobile AR using life-sized human avatars show that people estimate the egocentric distances of the human avatars accurately using mobile AR displays. Also, it has been found that an added avatar motion, such as walking side by side, has not improved the accuracy of the estimated distances of the avatars using these devices. Now, if you look on the results of both studies, you can find that 10 meters was used as the minimum testing distance for both of them. So, what have we done? We have added a coughing animation to a life-size static human avatar and have tried to see whether it has any influence on distance estimation or not. Also, the distances that we have tested are relatively nearer to the participants, such as 4 feet, 8 feet, and 12 feet. Now, to make it more relatable with the current pandemic situation, we have added masks to the avatars, which gave us 4 different avatar conditions, such as unmasked static avatar, unmasked coughing avatar, masked static avatar, and finally, masked coughing avatar. Now, a question naturally rises up, which is, why have we chosen a coughing animation and mask in our experiment? This is because, first, we wanted to see whether an evocative motion cue, such as the coughing animation, has any effect on distance estimation or not, rather than a simple walking animation. And second, some of the previous researches show that people perceive threatening objects as closer than non-threatening objects. In our experiment, the coughing animation would be the threatening situation, rather than the static animation of the avatar, where the mask may or may not reduce the effect of the scariness of the participants. This is the reason why we chose the coughing animation along with mask conditions in our experiment. So, what are the hypotheses of our study? First, given recent work on distance estimation in mobile AR devices, participants will be able to accurately perceive the distance to virtual avatars displayed in action space. Second, a coughing unmasked avatar will cause an emotional reaction in subjects that will cause them to perceive the avatar as closer to them than it actually is, given that they will want to ensure a safe distance away from an unhealthy avatar. To check that, we built a mobile phone app for conducting the experiment. Because of the pandemic, we were unable to run this study in our lab, and that's why we distributed the app via the Google Play Store and the Apple App Store so that people could easily install and run the app in their devices wherever they want. At the end of the experiment, the app automatically sent the data back to us via email. There were 24 trials in total in the experiment. Every trial started with either a masked or unmasked avatar randomly chosen by the app, and then either a static animation or a coughing animation was added to the avatar randomly by the app. Then a random distance among the three distances was chosen by the app, and the already chosen animated avatar was placed at that distance from the device. Next, the participant was asked to enter the egocentric distance of the avatar using the graphical user interface of the app. And then the app asked the participant to rate his or her comfortability level around the chosen avatar at that particular distance using a 5-point Likert scale, where 1 means very uncomfortable and 5 means very comfortable. These steps would go on for 12 trials. After 12 trials, participants were asked to walk 8 to 10 steps forward, turn back, and redo the experiment for up to another 12 trials. We did this to reduce participants' abilities to use environmental elements as references for the distance estimation across all trials. At the end of the experiment, participants were asked to rate their overall comfortability level around each avatar condition based on the same 5-point Likert scale mentioned before. We recruited 38 participants from USA, Europe, and Asia to run this experiment, among whom 6 participants' data were discarded because of faulty data. So, among the left 32 participants, there were 14 females and 18 males of age range 19 to 69 years. We ran a 2x2x3 repeated measures ANOVA on the mean distance estimations, and we found that the estimates were quite accurate with respect to the real distances without having any effect of the coughing animation or the mask and unmasked conditions. We ran a 4x3x2 repeated measures ANOVA on the ratings of comfortability of how comfortable people felt around each avatar condition in each trial by making the masked static avatar as the control, as we thought that this avatar condition will seemingly be the most comfortable choice by the people among the other 3 avatar conditions. And we found that the unmasked coughing avatar got lower ratings compared to the masked static avatar. There was no difference between the other 2 conditions, that is, the unmasked static avatar and the masked coughing avatar compared to the masked static avatar, which suggests that people felt comfortable around the masked static avatar in general. And finally, the level of comfortability increased with increment of distance for all our animation conditions. So, what have we found from the results of the experiment? First, people perceive the egocentric distances of the avatars accurately in mobile AR devices, which supports our hypothesis 1, which also says so. Second, we have not found any effect of avatar animation and mask on estimated distances, which is contrary to our second hypothesis, which states that people will perceive the unmasked coughing avatar to be closer to them than it actually is. However, we also have found that the unmasked coughing avatar got lower comfortability ratings than the masked static avatar, and the comfortability ratings increase with the distance increment of any avatar condition, which partially supports the second hypothesis, that is, the coughing animation and the mask conditions of the avatars did cause an emotional reaction in the subject about their unhealthy or healthiness. So, what could be the possible reasons behind our findings? First, there could be perceptual distortions that result from a viewpoint in the real world that is offset from the viewpoint of the device. This conflict in the center of projection would predict distortions which would expand the perceived environment, which might be the result of the accuracy in the estimated distances. And lastly, people might not encode the status of the virtual avatars, but rather just focused on their feet and estimated ground distances to them, because of which there was no effect of animation or mask on the estimated distances possibly. Finally, what can we take away from this study? First, it is possible to run controlled AR action studies in the wild using mobile AR devices if a user-friendly guidance to run the app and a reliable data collection method have been found. Finally, the results of our study replicate the results of the previous distance estimation studies conducted in mobile AR, which were controlled studies. However, our study was run in uncontrolled distributed environments. I would like to thank our sponsors and my co-authors for their continuous support throughout this study. I would like to thank you for listening to my talk, and I am happy to take questions now. Lastly, if you want to try the app in your phone, you can scan this QR code to install them in your device. Thank you and enjoy running the experiment.
Thank you, Saujajit, for the talk. I'm sorry if I mispronounce your name. I'm really bad with pronunciation. So we have a couple of questions for you. I think the first one would be, do you think that differing opinions about the pandemic could have impacted the way that people responded? And how so?
Yeah, so that's why we have to run the study in the wild, and people didn't come to our lab. And also I think people are well aware of the 6 feet distances, so that's why we chose to sample the distance over there so that we can get a kind of a result which they are not familiar with, but still we found an accurate result over there.
So how far into the pandemic was this study run?
We ran this experiment last year, and when the peak was kind of high, and yeah, so we have got the result during then.
So do you think the results would be different if you had run these studies in a lab in a closed space?
So we already had run a different experiment. So in 2019, so where people used to come to our lab, and we ran the study in a lab environment, in control study in an indoor environment and an outdoor environment. So, but still we got the same result, like the people used to accurately judge the distance properly. So I don't think it will change, but yeah, obviously, as this is a very remote environment and we do not have any control on the environment, so it is better to check it in future, like whether the environment and all other stuff has any effect.
And do you think that this evocative motion cues would actually affect distance estimation if the AR device used was not a mobile phone, was like a mounted display? Do you think it would be different the way people perceive the distance estimation and the threatening persona?
Yeah, so if you use HMDs in place of mobile phones also, and we know the field of view is lesser than the mobile phone for HMDs. We have found that some people are actually looking at the ground, like where the ground contact is. And my friends used to say like, oh, as you asked what is the distance between the avatar, so we didn't actually pay attention to whether it is coughing or not. So I don't think like it will affect the result, but yeah, if it is a real world environment, like people used to come to our lab and then we do the same experiment in real world with real people, then maybe like it will affect the result, I guess. But in AR or virtual world, I don't think it will affect mostly.
So one last question, actually two last questions that we have for you. What are the challenges of running AR studies in the wild?
Oh, there are lots of. So first of all, the data collection method. So you have to build a very reliable data collection method, because you don't know like what is the internet connection the participant is using during running the study. So you need to make sure the internet connection is stable enough. And if it is not, then you need to make sure like you have to get the data back properly from them. And you have to give them a very detailed guide, like how to run the experiment and when to do what. Otherwise, it is like really problematic for the experimenter, like how to run the experiment. So I think also we got a problem with Apple. So Apple, whenever Apple saw our experiment, they thought that we are misrepresenting the pandemic or something like that. And they, because of this thing, they thought that this is going to be a security issue, and they didn't allow to publish our app directly on the Apple's App Store. But they fortunately allowed us to beta test the app, and that's why we took that link and share it with our participants. But Google allowed us to release that app on the Google Play Store. So it is live now.
And what recommendations would you give to people that are thinking about running AR studies in the wild?
I cannot get it. It was glitchy.
I'm sorry. I asked what recommendations you'd give to people thinking about running AR studies in the wild.
I would say first of all, you have to build a very interesting graphical user interface and easy to use graphical user interface to help the people to easily like go through your app properly. And second is the data collection method. So you can use email or Google form, something like that, to use like to get the data. And yeah, these two basically mainly. And obviously like interactive way of teaching people how to run your application and send the data back, like maybe giving some sort of notifications that you have to do that, or maybe giving some pictures, videos, GIF files inside the app, so they do not have to go from here to there to understand like what they need to do. So everything, if you can embed in the particular app, that will be great.
So in your particular app, how did you train participants how to use the application?
So before starting the actual like experiment, I walked through the whole experiment with them, with some trials, with some random trials, and like what they need to do. Like say suppose, for example, if they need to sail, if they need to like when I was asking like what is the distance of the avatar, so then I am just pointing in the GUI that okay, just press on the button and then give your answer like this. And then when I was saying like you have to move backwards and like walk 8 to 10 steps forward, so I am giving the information, okay, now move back, move 8 to 10 steps forward and turn back. We do not know whether the people actually have done that, but we think like the people moved 8 to 10 steps forward and turned back. But yeah, like in this wild experiment, it is hard to actually monitor the people's activity, but we are guessing like by using the informative and instructions, it will be helpful. And I have faith on them, kind of.
So thank you. We are right on time here. I really appreciate your time with us and answering all the questions. So right now we're gonna have a break of 30 minutes. You can meet us in the Gather Town, I think Piazza. So we're gonna be there so we can talk more and answer more questions.
Okay, thank you.
See you guys.
Dr. Ed.
Okay, that's because Zoom is, can you hear me now? Yeah, Zoom is fighting for my microphone. How do I change my name?
Right, or click on, hover over your name and then click on more.
Okay, I see. So 3 dots. Oh, you changed. Let's see. Hey, Missy. Her hair is longer and longer. Okay, that's because Zoom is, can you hear me now?
Wait, I can hear you. Who are you talking to?
Yeah, Zoom is, that's me from like a minute ago. Rename, here we go. Okay. Okay, Arifin, you became a second person and I've taken over your body.
Hey everyone, I'm just wondering why I am twice in the Zoom actually. So just got that.
I was trying to get in here as a panelist.
Okay, yeah.
So the other issue is it looks like my background is backwards. Why would that be?
It looks good from this side.
It looks good for you guys?
Yes.
Okay, it looks backwards to me, but.
It's actually mirrored, so.
Okay, I see.
Hello, everyone.
Okay, I appreciate it. I needed to get in here somehow, or at least make sure I could get in here.
We're gonna wait just 1 more minute so we can continue with the presentations.
Okay. All right, so I guess I'll get out of Gather Town. All right. How can we tell how many people are watching?
In Zoom, there's you can click on participants and it'll show the number of panelists and the number of attendees. There may be a way to see on YouTube as well.
Yeah, we're also streaming on YouTube, I believe.
Yeah, let me see if I can find that out.
The world is watching, Ed. Okay. Hello, Bobby.
So I think we can go ahead and start the next presentation, but we're gonna switch the order of the paper. So now the paper that is gonna be presented is gonna be by Mohammed Arefin from Mississippi State University. The paper title is Effects of Distracting Background in Focus Switch Distance in Augmented Reality System. Just 1 second.
Hello everyone, I'm Mohammed Arefin. I'm a PhD candidate from Computer Science and Engineering Department of Mississippi State University. Here, I'm going to present our paper named Effects of a Distracting Background and Focus Switching Distance in an Augmented Reality System. The authors of this paper are Mohammed Arefin, Nate Phillips, Alexander Plowski, and J. Edward Swan. In this presentation, at first I will start with the problem statement, then I will talk about the previous work, and after that I'll briefly describe our experiment, and I'll finally talk about our experimental results and the discussion. Most of the currently available optical see-through AR displays have a fixed focal distance which ranges from 1.25 meter to the 2.5 meter, which brings the issue of focal distance switching. Focal distance switching means accommodating between two focal distances to see information with a sharp focus. From the focal distance switching, we get the focal switching distance, which is the absolute difference between the previous focal distance and the new focal distance. Now, if we look at these pictures are taken from a YouTube video where a person is wearing a Google Glass and walking in an urban street. What we observe from this video is that when the person focuses background, his foreground AR information becomes blurred, and when the person focused on the foreground AR information, his background becomes blurred. Therefore, to integrate information, this person needs to switch his eye focus back and forth every time between the two focal distances. Another important issue is the real-world background effect. We know that real world is very complex and dynamic. It has different type of objects of different color, different shapes. Also, the objects can appear at any distances from the user. We don't have any control on the real world environment, and the lighting condition also highly fluctuated. Therefore, it is very important to consider the real world background effect while designing the AR interface. In 2018, Gavard, Meher, and Swan investigated the AR display context switching and focal distance switching on human performance using a microvision nomad AR display and with a text-based visual search task. They found a significant negative impact of context switching and focal distance switching on human performance and eye fatigue. However, this research have some certain limitations, and one of the major concerns is that their experimental findings may be related to their experimental display. Therefore, in 2020, Arifin and his colleagues replicated the text-based visual search task on a very different AR display on AR haploscope. And they've generalized the issue of focal distance switching in an AR user interface design. So in the pictures, you can see that participants are wearing two different type of displays, and both experiments are totally different and done in two different conditions. However, if you look at the graph or the results, they have the similar type of finding. What they found is that due to the focal distance switching, participants more likely to miss the target letters when it appears on the first line of the text. Therefore, we can say that previous research has found a significant negative impact of focal distance switching on eye fatigue and human performance. However, these results are based on a solid background and no distracting features were considered. Furthermore, in 2007, Gavard and his colleagues investigated the effect of text drawing styles and background on human performance using the same text-based visual search task. They have found the evidence that background, text drawing style, text color have a significant impact on user performance. However, they didn't consider the focal switching distance in their experiment. Therefore, we can say that no previous work examined the effects of both focal distance switching and complex background together in the experiment. Altogether, we have set up our research goal. Our research goal is to systematically investigate the effect of a distracting background and focal switching distance in an optical see-through augmented reality system. We set up our hypothesis. We have two hypotheses. The first hypothesis is that, consistent with the previous work, increasing focal switching distance reduces task performance and increases eye fatigue. Our second hypothesis is that a distracting background further reduces performance and increases the eye fatigue. To explore our research question and to test this hypothesis, we have considered AR haploscope as our experimental display. AR haploscope is a very powerful and dynamic display because it has the capability to dynamically change the accommodation and verdance demand. Also, this display can be adjusted for a wide range of IPDs. We have adapted the text-based visual search task from Gavard, Meher, and Swan, and in here, each task has 5 subtasks and 25-second time pressure was provided. So, in this presentation, I'm just showing you one single subtask here. Participants were instructed to focus on the right text at first and find out the target letter. target letter is a side-by-side identical letter. For example, here the target letter is O, because the small o and capital O is side by side. And then the participants are instructed to focus on the left text and count how many times it appears on the left text. Here the answer is 1. And after getting the number, participants were instructed to use a numeric keypad to provide their answer. So let's talk about our experimental variables, which is starting with the independent variable. So we have the focal switching distance, which was our continuous independent variable. We have real text distance at three levels, 0.67, 2, and 4 meters, and we're similar for the air text distance. As I mentioned previously, that focal switching distance is basically the absolute difference between the previous focal distance and present focal distance. Therefore, we have the focal switching distance was either 0, 1.332, or 3.33 meter. We have another independent variables, which is the categorical independent variables background. We have two types of background, blank and the distracting. During the blank condition, subjects will observe the textual information on a solid black background. This is basically our control condition. In a distracting condition, a complicated urban scene background was considered, and participants observe the textual information on that background. And if you look at that, you can see the different composed of building, text, and sign, and different distracting elements are on the background. We have measured how many subtasks are completed by the participants and how many of them are correct. We also gathered the eye fatigue information from the subjects by using a 7-point bipolar rating scale, where 1 means very low fatigue and 7 means very high fatigue. This is our overall experimental setup. Here you can see that subjects are looking through the AR hyperoscope for the AR text, and the real text was presented on a physical monitor. So we can move the monitor at any of the 3 different distance levels, and AR text can be presented at any of the 3 distance levels. In our experiment, we have considered 8 participants with both normal and corrected vision, and age range from 24 to 54. We have considered within subject experimental design, and all the experimental variables are properly counterbalanced. Therefore, each subject observed 90 tasks. Note that each task has 5 subtasks. Let's talk about our analysis and results. To analyze our results, we have considered the multiple regression method described by PercxR. We considered 3 steps to determine whether a linear model that best fits the data or not. At first, we tested the slope test, which indicates the slopes of the tested linear fits significantly differ or not. If the slope test is significant, then we haven't done any other testing. If the slope test is not significant, then we test the intercept test. If the intercept test is significant, then the 2 fits with a common slope are reported as the best overall description of the data. If the intercept test is not significant, then we use a simple regression for describing the overall description of the data in the experiment. We also reported the effect size of R square and dr square, where R square is the overall percentage of variation explained by the linear model, and dr square is the percentage of variation explained by the categorical variable. Now let's look at our results. Start with the task performance. Here is the table and the graph for our task performance result. Let's look at the graph at first. Here the x-axis showing the different focal switching distance amount in meter, and y-axis showing the number of subtasks. We have 2 panels, one for the completed, another for the correct. You can see 4 different colors here for 4 different levels of the focal switching distance, and the shape is basically indicating the background blank or distracting. And the table is showing their F values here. So you can see in our graph that we are just reporting a single linear regression line here because we haven't found the significant slope different, significant interface different. Therefore, we are just reporting here the simple regression equation here. So we can say that we did not observe an effect of a background on performance in this case. However, if you look at the linear regression line, you can see that as the amount of focal switching distance increased, number of subtasks completed decreased, and as well as the accuracy also decreased. Let's look at the eye fatigue. Here, similar to the previous graph, you can see that there's only a single linear equations are here because we didn't observe any slope difference and intercept difference significantly. Therefore, there is no interaction effect, no effect from the categorical variables, and only the main effect of focal switching distance exists. Therefore, we can say that we did not observe the effect of a background on eye fatigue. However, we can see that as the amount of focal switching distance increased, participant eye fatigue is also increased. So, the results of our experiment support our hypothesis 1. Therefore, increasing focal switching distance reduces task performance and increases eye fatigue. However, the results do not support the hypothesis 2. A distracting background further does not reduce performance and increase eye fatigue. There could be two possibilities. One is there is no such effect. Other is the effect was too small to be detected by our sample size, which is one of the main limitations of our study because we have considered only just 8 participants, and which brings the idea of our future work. In a future study, a larger sample size can be considered to investigate this background and focal switching distance effect together. Also, in our experiment, we have considered a single complicated distracting background, but in future, in other study, a sample of different examples of background could be considered for investigating this problem. And binocular eye tracker could be integrated in the experiment to track the participants' perceptual depth changes during the experiment. That's all from my part, and if you have any questions, I'll be happy to answer that.
Thank you, Arifin, for the great presentation today. We have a couple of questions for you. The first one, why did the subtask text switch from upper and lowercase to just uppercase letters? Because that's what it looks like on these slides.
Actually didn't get. Could you please repeat the questions again?
So why the subtask and the task switched from upper and lowercase to just uppercase letters?
Oh, so this task, we actually adapted this task from the previous work. Previously, this task was designed by the Gavard and his colleagues. So this task was designed in such a way that you need to search the word, you need to find the target letter at first. So you need to find how we can define the target letter. The question is that. So we define the target letter in such a way that a small letter and capital letter is such side by side. Same letter, capital version, a small version. So that's how they defined the target letter. We adapted that in our experiment, and that's how we consider the target letter and not like other rules for that. That's a great question. Thank you.
Thank you. We have a question from the audience, from Alsti. First of all, great presentation. Do you think the results would be different in dynamic backgrounds were used, or perhaps static 3D backgrounds?
Yes, the answer is yes, because of the previous work. So previous work by Gavard, Dr. Swan and others, they found the effect of different background, different text drawing styles, and they also mentioned about the dynamic environmental lighting, dynamic environmental conditions. So based on that perspective, I can say that yes, there could be a chance that there should have impact on the performance. However, the experiment we did, we haven't observed the effect. But further potential experiment could be done by considering a very dynamic background or 3D background, or whatever it is. But if the potential experiment could be done considering this effect.
I can
and also, do you think
add to that a little bit? So the big issue is it needs to be done outside. This was discussed with the last paper as well. It's hard to do these things outside, but that's where this work really would need to go. Outside.
And do you also think that the results would be different if you had added a new task? For example, you're doing this visual search task while driving, So do you think you'd find the same phenomena that you found here?
Yes. Yeah, that's actually a great observation. Like what is the one of the potential application for this kind of findings? So one of the potential application is AR head-up display. Like if you consider AR head-up display, then where the information is not presented at the same focal plane. So you have a particular fixed focal plane and the real information is presented at different distances. So you are continuously switching your eye focus and driver's attention. So this is one of the potential application of our findings, like how the focal switching distance impact on the potential AR applications and development of those applications.
So yeah, nice. Thank you. Just one last question related, kind of. So you mentioned that future work would include the eye tracking device. Yeah. So what are you interested to measure using the eye tracking for this type of study?
So eye tracker is like, you can get different eye related parameters. So one of the parameters is we need to track the perceptual depth change. So as we are saying, subject change their eye focus from one distance to the another, but we are not actually tracking that quantitatively. We are just saying and we're observing based on that, and we are not fixing that. Okay, we are, fixing in sense that we are not confirmed that they actually properly switch that. So in order to track the perceptual depth changes, we actually need a binocular eye tracker in future. Also, this could be considered to measure the eye fatigals, because the pupil size which changes with the fatigue. So if we want to measure the pupil size objectively, not subjectively, then the binocular eye tracker is very needed.
So this was one of my questions. We believe that participants can actually measure and report fatigue of the eyes.
So previous experiments successfully did that, and that's how we actually believe on the subjective rating. But the previous researchers and they are saying that objective measurement could be done. However, I found some related work related to this objective and subjective measurement, and researcher mentioned that there's no significant difference between these two. But if we have a subjective rating as well as we have a quantitative rating, obviously it will increase our confidence on the eye fatigue rating of the subjects.
All right, can I add to that?
Yeah, sure, Greg.
So, we of course ran ourselves through this experiment too, as part of developing it. And this task really does make your eyes tired. After you do it for a while, you can really feel it. And in part, we designed the task to be fatiguing. And the comments from the participants also indicated pretty definitively that it was making their eyes tired. So we have high confidence they were actually getting fatigued.
Okay, thank you. Thank you very much. You're right on time. I'm sorry we had other questions, but we need to move on. Thank you very much for the great presentation. So the next presenter is going to be Jonathan Flittner from Virginia Tech. The title of the paper is Adapting Image Analysis Measures of Visual Clutter to Multiple Plane Augmented Reality User Interfaces. Just one second.
I'm Jonathan Flittner, and today we'll be discussing my research of adapting image analysis measures of visual clutter to multiple plane augmented reality user interfaces. Augmented reality research is important as it is a rapidly growing technology that is seeing use in an increasing variety of domains and applications. The proliferation of augmented reality means a steep increase in people dealing with AR user interfaces and an urgent need for better methods of designing and evaluating these interfaces. We also need a better understanding on what factors of an AR UI affect user performance. The difficulty in accomplishing this is that AR UIs are inherently different from traditional user interfaces. A major difference is that the content of an augmented reality user interface can have multiple depth properties, meaning objects of interest can appear at multiple depths from the user. The end goal of this research is to build an equation that qualitatively evaluates augmented reality user interfaces and gives a single number ranking for a given user interface. This helps in augmented reality user interface design by allowing us to rapidly test and compare different interfaces by eliminating the need for some subject testing. Another benefit is the opportunity to use this clutter score algorithm as a real-time evaluation tool for AR UIs. The current computation time for the clutter score algorithm is rather low, so it could be used to help in applying dynamic AR UIs. In this study, I used the image analysis measures of feature congestion, subband entropy, and edge density to characterize the clutter of an image array. Those methods were chosen since they have been shown to correlate with visual search time in traditional user interfaces, as well as being good candidates for AR user interfaces, since they do a better job of capturing the clutter of naturalistic images, as opposed to other clutter measures such as set size. Feature congestion is a single number rank of clutter based on weighted measures of color, luminance contrast, and orientation within a scene, or in this experiment, an array of objects. It serves as an algorithmic summary of the difficulty in drawing attention to an object added to a given scene or object array. As the amount of objects in a scene increases, it becomes more and more difficult for the user to identify and find objects. Subband entropy is a measure of how efficiently a computer can encode an image. The theory is that humans go through a similar encoding process when seeing an image, so the more cluttered an image is, the more complex and difficult to encode it will be. Edge density uses an algorithm to determine which pixels are edge pixels, then density is expressed as a percentage of edge versus total pixels. The theory is that the more edge pixels, the more distinct object the eye picks up, and the more cluttered the scene appears to be. For this experiment, subjects used only the HoloLens to display the target images and image arrays, and a Bluetooth keyboard to use as an input device for the HoloLens. The variables in this study were the clutter level of the array, the number of augmented reality user interface planes, the array of the AR UI planes, and the plane that the target object was located in. The task that subjects had to complete was to find a target object in an array of objects. Objects came from a set of general household objects and were size corrected so they all appeared about the same size. The subject was first shown the target object, then when they were ready, they used the keyboard to advance to an array of objects, and then used the keyboard again to indicate when they had found the target object in the array of objects. All targets and objects were two-dimensional and generated with the HoloLens. The following slides will be an example of what the subject would have seen. The target object would appear in the center of the field of view of the subject, and when they had familiarized themselves with the object, they would then advance to the array search. The background for the subject was a plain off-white wall. This is an example of the array the subject would then search and would indicate on the keyboard when they had found the target object. Note that this is the straight-on view of the object array, but in practice, the objects would appear to be on different AR user interface planes. They would appear to be at different depths from the user. As seen here, the perspective view shows how the objects would be created by the HoloLens at different AR UI planes. In this example, we would have AR UI planes at 2 meters, 4 meters, and 6 meters. To generate the object arrays, first, clutter levels for 45 objects were determined by analyzing the edge density, subband entropy, and feature congestion scores for each object. These measures were then combined into an overall clutter score for each object. Objects were then ranked from least cluttered to most cluttered, and image arrays were created by arranging sets of 36 objects on a 9x5 grid. The lowest 36 objects were used to make low clutter arrays, and the highest 36 to make high clutter arrays. Arrays were created using Excel's random number generator function to assign an object to a grid position, and in the case of multiple planes, to assign an object to a plane. The random number generating function was then used to select which object will be the target object. In the scenarios involving arrays made up of objects on multiple planes, arrays were generated so that no object would be in front of another object to avoid occlusion issues. Arrays were then analyzed to check for within clutter level consistency, as shown on this slide. The results of response time versus different study variables are shown here. As expected, higher clutter had a higher response time. Also, as would be expected, response time increased with the number of planes, but there was extremely high variability to this. The actual array of the augmented reality user interface planes did not seem to matter as much as just the number of planes in general. The exception to this is when arrays were at 4 meters and 6 meters versus the other 2 plane arrays, and this could be because objects farther away may be easier to search for without the distraction of near-field objects. A Pearson correlation test was then carried out between response time and image analysis measures for the combined plane arrays, all objects, just the objects of the target plane, and just the objects of the non-target planes, and for the image itself. Correlation was found for image analysis measures for the combined array and for just the target itself. This is an interesting result since we can interpret it as being that only the total amount of clutter that matters for visual search time, not the clutter of the AR/UI plane and not the clutter of the non-target planes. The strong correlations of target clutter to response time is interesting because it shows that the clutter of the target has a large effect on how hard it is to find. So the more complex a target a person is searching for, the longer it takes to locate. Lastly, it is good to note that while all image analysis measures correlated rather equally, edge density was slightly ahead of other measures. This is useful since calculating edge density is less computationally intensive as feature congestion and on par with subband entropy. So in applications where computational time matter, it might be possible to just use edge density as a stand-in for other measures. In conclusion, image analysis measures are still valid tools for multi-plane augmented reality user interfaces, and target clutter has a larger effect on response time than previously thought. Future work will be to expand this research from 2-dimensional objects to 3-dimensional objects and from 1 to 3 plane AR/UIs to AR/UIs comprised of objects on a continuous depth spectrum. We will also look more into the effects of target clutter on search time, and lastly, we will move to studying naturalistic AR/UIs, searching between a mix of 3-dimensional virtual objects and real objects. I would like to thank Dr. Gabbard for his guidance and support throughout the study, along with the Cogent Lab at Virginia Tech and the Grado Department of Industrial and Systems Engineering at Virginia Tech, without whose help this work wouldn't have been possible. Thank you all for coming to my talk, and I would be happy to take questions now.
Thank you, John, for the presentation today. The first question that we have for you actually came from the audience, Dr. Ed Swan. So he says, here depth planes are to be displayed by stereo disparity, but not accommodativity. Is that correct?
Yes, that's correct. Based on the limitations of the HoloLens hardware.
He says it would be interesting to compare to real matrix or semi-transparent displays where both a stereo disparity and focal distance could vary. So
yeah,
I'm sorry, go ahead.
Oh yeah, I was looking into maybe using the magic leap to do this because it has more focal abilities, focal point abilities.
That's 2.
Can you repeat, Dr. Edson?
Oh, well, the magic leap has 2 focal planes. And so indeed, you could replicate it, with 2 different accommodative distances.
Mm-hmm.
So a next question for you. I don't think it was clear how did you differentiate clutter levels of low and high? What was the difference between them? The threshold, I would say.
The threshold was just I did the image analysis measures of clutter for 45 objects, and then they're on different scales. So like feature congestion spits out a rating of 6.5, and edge density would spit out a rating of like 0.003%. So I tried to get all numbers like on an equal 0 to 10 scale, added them together, and then I took the objects with the lowest, additive clutter scores and the objects with the highest additive clutter scores, and then made arrays with those 2 different sets. But there was some overlap in objects in each set.
Okay, thank you. So you mentioned that the goal of this study was to develop a qualitative model, right, for evaluating AR interfaces related to clutter. And you mentioned 3 factors that you're using here, which are edge density, feature congestion, and subband entropy. So what other factors you think would be good candidates to include in a model?
Set size is always a good factor just because it has a strong correlation, but set size, I want to expand it to also look at the clutter of the background and not just of the display. And set size really starts to fall apart when you view a naturalistic image in terms of clutter, because then you have to define what an object is and how that like how many sets are in an object of like a room. Is an object a chair? Is an object a table? Is an object a set of chairs and tables? So I wanted to keep it more general in that, so it could be applied to, naturalistic scenes.
So how was the laboratory design that he used? Like there was no background, the background was white. How was it?
The subjects just faced a plain white wall, and the objects were projected. If they were 6 meters away, they'd almost be behind the wall, but into the wall, just like a neutral, very, very neutral background that wouldn't really have any effects.
Okay. And also I have a question related to your model, because you showed the factors and also you mentioned that you'd give some weights to those factors. How did you give those weights to the model?
So I'm weighting it right now and just kind of updating the model to be what's the most important factor. So I'm trying to see what has like a sensitivity analysis almost of what has the largest effect. And then that's going to be weighted higher based on a sensitivity analysis. Currently, as I go through the data more and more, it turns out the clutter of the target itself seems to be one of the more highly rated factors. So in that case, the target clutter, so the clutter of what you're searching for, is going to have a much higher weight than something like target distance from user, like depth distance, not XY distance.
Okay. And I don't think you mentioned that in your presentation. How many participants you reported in this study?
Only 12. It was a rather small study. I'm hoping to expand it more now that things have, opened up a bit more.
Oh, yes. So we have a question here for Dr. Edson related to your model again. So he says that the model appears to be additive. Has an interaction model been considered?
Oh, yeah, I was very unclear about the model. That model is really it's just my general stand-in so far, but I think interaction model is going to be much more appropriate because there are some interaction effects that, cluttered object is going to be harder to find in a high cluttered scene. So it's probably not going to be strictly additive. It definitely is going to end up being interactive.
Okay, I think we are almost on time. Just one last question.
Mhm.
In your results, you showed time to find the target in terms of means. Did you conduct
Mhm.
any other analysis to find statistical significance of your results or not?
I've been doing more statistical analysis, but just, reaction or like search time is basically the only thing I have. We're just looking at search time, average search time. That's it.
Okay, thank you.
Keeping it
Thank you very
single
much
number.
for your
Oh, thank you all for coming, and I'll try to make
Thank you very
any more
much for your
presentations.
presentation today and answering the questions. I think we are right on time here.
Awesome.
So
Thank you.
I'm gonna give the stage to Dr. Missy Smith so she can continue.
Yeah, thank you, Naira. So I'm just here to introduce Ed Swan, who is a professor of computer science at Mississippi State University. And his research, as we've seen through some of the presentations and other discussions and citations, has been focused in human factors investigations of computer-generated graphics. He also, as a fun fact, was one of the original founders of the PERCxR workshop. So in 2015, he, Kiyoshi, and Ernst started up this event that we're all at now and continuing in new ways with a little bit expanded scope. And that was also my first session. I didn't realize it until I was kind of digging into it. And also Ed is a longtime mentor and a good friend. And so I just am excited to introduce him, and I will give you the floor, Ed.
Can you all hear me? And can
Yes,
you
we
see
can hear
me?
you.
Okay. And you can see me? And I'm
Also,
not
yes.
backward, and I'm not backwards looking. So
You're
I got-
right ways.
okay. So I look backwards here, like looking in a mirror, I guess. So let me find the right screen to share. Okay, so you should see like a zoom and stuff, but now let me replace that.
Actually, we see your useful commands. I think we see a different screen.
Yeah, that you see the screen I want you to see.
Okay,
And
cool.
now you should see my slide.
Yes.
Okay. Now let me arrange a couple of other windows here to make this correct looking. Okay, so I'm going to give a talk about how the social network of knowledge leads to scientific truth. I very much appreciate being given this opportunity to give a keynote talk. And it's an opportunity to talk about something that I'm currently interested in and passionate about. So this talk is not going to be an overview of work that has been done in my lab. That's another kind of keynote talk that's maybe more often given. It's instead going to be about a philosophical question that I've been thinking about for a while and also talking to other people about. Oh, and I also want to change my camera so you don't see the side of my face because I'm going to be looking at a different monitor. So let me try to do that. And now I can look here and it looks better, I think. Okay. So this talk is inspired by the concept of reproducibility in empirical science. In 2018, I first offered a tutorial, first at VR that year in March, and then later at ISMAR that year in October. And that was called The Replication Crisis in Empirical Science, Implications for Human Subject Research and Virtual Environments. Since that time, variations on that tutorial have been offered 6 times, the last 3 times in collaboration with Arifin Mohammed, and even this week on Monday as the ISMAR workshop on replication in extended reality. But the impetus for this series of tutorials began over conversations with colleagues at this conference as well as the VR conference. Usually these conversations were over food and beer, and we talked about these ideas and these issues for a good 5 years before one of them was tutorials chair one year and asked me to put the thoughts together into a tutorial. And I just want to point out that, you know, that's what we're missing this year and have been missing for the past year and a half, the spontaneous idea generating conversations. Really, in some ways, the most important activity of a conference. So I hope we're back to that very soon, hopefully by March or so of this next year. Now, by empirical science, I mean conducting an experiment. When we conduct an experiment, how do we know that we have true knowledge? So the knowledge is assessed, if it's in an experiment, from a hypothesis test. And if the p-value that we find is less than 0.05, then it's relatively easy to publish the experiment. We call that a significant result. And furthermore, if we have some idea of the effect size that we're looking for, and we have the alpha level set to 0.05 and the beta level set to 0.20 or less. So this is the recommended balance between the probability of a type 1 error and a type 2 error. We can have about as good of a confidence in the result as we can in an empirical experiment assessed with a hypothesis test. But the thing that I'm interested in this talk is to further ponder the question, does that mean that the knowledge is true from a single experiment? And the answer is no, that's not what it means, because the reasoning from an experiment is probabilistic. The reasoning is not absolute. And so the best you can say when looking at a result from one experiment, and that's the case with the, the papers we just heard, and as part of this workshop, all single experiments, if I'm remembering correctly, we have some confidence that the knowledge is true. Now, if the experiment is repeated by others, this is the idea of reproducibility, and the result is reproduced, then what that means is our confidence that the knowledge is true increases. Now, eventually, if a result is repeated again and again by different groups, we really start to believe that the knowledge is true. So, for example, in our field, the idea that location of virtual objects is misperceived in some way, generally underestimated, that's been replicated by many of us in this field and related fields over many different years. And we really believe that that is true because of the replication. So that leads to the question, does empirical science lead to scientific truth? Now, our professional community consists of a gathering of both scientists and engineers. And I think to a degree, all of us in this community are some combination of scientist or engineer. Some are more on the side of the engineer, some are more on the side of the scientist. So I've always seen myself as a scientist, and I came across this quote, a very wonderful quote, maybe 15 years ago. And it's talking about the difference between a scientist and an engineer, especially in a field like ours, where both activities are part of the intellectual questions that are asked. So an engineer is someone who studies in order to build something. And a scientist is someone who builds something in order to study. Now, I first heard this truth, as I first heard many truths, from my long and wonderful times collaborating with Stephen R. Ellis. But I then found out that Steve got it from Fred Brooks. So both men are sources of wisdom, certainly in our field. So over the summer, I found this book, and this book is what this talk is based upon. I found this book because I heard the author discussing these sorts of topics on a podcast. And I realized this guy, who is basically a philosopher, has been thinking about things like scientific truth. And I got the book and I read it, and I just became very excited because it's a philosophy book, but it speaks about these ideas. It's connected to these ideas. So it's a book about philosophy. Long time ago, as a college student, I took a philosophy class, but it didn't really stick. I couldn't really connect whatever that class was about to stuff I had been thinking about at the time. That was like 35 years ago. So when I was given the very nice opportunity to give this talk, I decided to make a talk about this because I was excited about it. And this talk gave me the excuse to spend a week or so immersed in this scholarship. And as all of you who are professors or teachers know, you really learn something when you try to organize it and present it and teach it yourself. And so the book talks about, and this talk talks about, how a social network of knowledge, that's what we're part of in this community, and that's what science is composed of, how that leads to scientific truth. So how do we know that science is true? So we can start by looking at the mighty examples of progress in human history over the past several centuries, and indeed over the past 12,000 years or so. So here's a graphic I found on the evolution of the technologies behind agriculture. And so, agriculture was the first technology that brought humans from small bands into, larger cities and allowed the specialization of tasks and so forth. And so we know that these technologies, the tractor, the water wheel, genetically modified organisms, precision agriculture, et cetera, these technologies have all been tested in the actual world against the reality of growing food and have been shown to be successful. We know they were successful. They are successful because there's so much food. In fact, for many of us, there's too much food and it all tastes so good. So the science behind these technologies must be true science. Otherwise, we would not see them working. And you can show examples of this in all sorts of different fields. So here's a kind of a timeline picture I found for medicine in Britain. We all live longer lives than we used to. So clearly, a lot of the knowledge behind medical science must also be true. And then a picture of Apple computers. I've been using Apple computers and also other types of computers, of course, but even when I was in high school in 1979, we had an Apple II computer that I used. So I've been using these devices for the entire span of time displayed in this graphic here. And then one more of these. Here is an example of the development of displays in our field, the virtual reality displays on the left, and then augmented reality displays on the right. So again, for all of these examples, the general message is that the technologies have been tested against reality and shown to be successful, and therefore the science behind these technologies, at least some of it, must be true science. So there are very compelling historical results as well. So I also teach classes in data science, and I go to this website, Our World in Data, all the time. I got a lot of data sets, and it's a cool place if you're like me. So here's the growth in world population the last 12,000 years, and you can see this enormous exponential growth in world population over the past few hundred years. And here we can explore that in more depth by turning the y-axis into a log graph, and then going from 1750 to the current day. And what we see here is the effect of the two big agricultural revolutions that have occurred since the 1700s. So first we have the second agricultural revolution, as it's called, which began in Britain. And we see a linear growth curve here in world population. And then about 1950, we see the effects of what is called the Green Revolution. And you can see that the slope, it remains linear, but the slope is steeper. Now, of course, linear effects against a logarithmic axis are exponential growth. So both of these are exponential curves, but the Green Revolution has increased the slope of the exponential growth. So if we think about these markers of development since the Age of Enlightenment, you know, these are some historical markers that have all been considered important revolutions over the past 350 years or so. And the agricultural revolutions I mentioned are primarily behind this growth in world population. Another example, we have a reduction of extreme poverty over the past 2 centuries. So in 1820, basically the great majority of the world lived according to some definition of extreme poverty or poverty. And it is greatly decreased over the past 200 and so on many years. Of course, even today, there's still too many people living in extreme poverty, but the message is it has declined, and it has declined rapidly. And so we can in part thank the development of market economics as the reason why so many people in the world, especially in Asia, over the past since World War II, you know, have moved beyond extreme poverty. That doesn't mean the problem is solved. I'm not trying to make that argument at all. And finally, let's look at the world economic growth since antiquity. So from the year 1 to current times, we see evidence of exponential growth, of course. And before about 1600, the annual rate of growth was close to 0. So here again, we've plotted against a logarithmic scale, and we see a little bit of an increase in the rate of growth starting in the year 1000. Of course, these estimates of growth back in those days are very much estimates, they're noisy. But what we can see is around the year 1700, we see a definite increase in the rate of growth. And so this would be a result of all of these milestones in the development of our modern world. And so the conclusion remains, as it did a few slides ago, that the ideas behind these revolutions have been tested against the reality of the world and the human existence and have been shown to be successful. Sometimes the success, I mean, it permeates our lives to the degree that we don't think about it. But, you know, it's really remarkable what's happened in the world in our lifetimes and the several generations before us as well. So the knowledge behind these revolutions must be true knowledge. So that brings up the next topic in this talk, and that is, what is true knowledge? True knowledge has been of interest to philosophers since the time of the ancient Greeks. So here is as described in a dialogue of Plato. And so Socrates and Theaetetus are attempting in a discussion, in a dialogue, to define true knowledge. In this case, Socrates is like the older professor type, and Theaetetus is the young student, and they are, discussing and learning together. And so they're trying to define true knowledge. And so the first hypothesis that they come up with is that true knowledge is correct perception of the world. But, and the problem comes up, perception varies between individuals and even within an individual. So there was a meme a few years ago on the internet, what color is this dress? And different people would see it as being different colors. And of course, those of us who have run perceptual experiments, which is probably everyone attending this workshop, we've seen that perception varies between individuals and within an individual, depending on other things. So that can't be the source of true knowledge. The next hypothesis is that true knowledge comes from true judgment. But the problem there is that sometimes a random or ignorant view can just happen to be true. You can be right about something for the wrong reason. So how can it be true knowledge if it's the result of a random or ignorant view? Then the third idea, true knowledge is true judgment with an explanation as to why it's true. The problem here is that how do you judge the truth then of the explanation? It leads to a type of circular reasoning. To know the truth of the explanation, you need to know the truth of the knowledge in the first place. So all of these are found in this dialogue to be unsatisfactory. None leads to true knowledge. So Socrates and Theaetetus end the dialogue not having established what true knowledge is, but having kind of put some boundaries on it and determining what it is not. So the idea of how truth is determined has been of interest to philosophers from antiquity through, for a long time, from antiquity. Now, from antiquity through the Middle Ages, the idea was that the state of human nature is hierarchical, and therefore truth is hierarchical. So the idea was that truth comes from the wise, the strong, the godly, the aristocratic. They determine the truth. And then the truth is given to the ignorant, the weak, the infidel, the vulgar, and so forth. So an important thinker of this time was Thomas Hobbes. In the mid-1600s, he published the work for which he is known today, a book called Leviathan. And he is considered the founder of modern political theory. Now, he did his work and he wrote his book during the English Civil War. That was a titanically destructive period in England. He was an English man. And he determined that the state of human nature is constant competition and rivalry, personal and tribal power structures. And so how could this be overcome? He was wrestling with the philosophical question in the middle of war. How can this be overcome? And he determined that truth is what the ruler says is true. And that's where his title comes from. The ruler is Leviathan. You have to designate a person, or in his world, God has to designate a person to be the ruler and determine what truth is. The problem with his account, as he and many other philosophers and others have determined over the years, is that truth cannot come from any single individual. And the reason is all of the individual biases that we all have. And so here's a list of all these biases. This is not a comprehensive list, but it's a pretty long list. I'm not going to talk about every one of them, but I'll mention a few that are relevant or have been apparent in the last few years of human existence. So One bias is availability bias, and that is that people tend to overestimate the likelihood of a disturbing event like a terror attack. Okay, they're actually very uncommon, but that's not how people think about them. A familiarity bias, that is believing things that one hears often, even if you hear about them because you're being told that they are false. Confirmation bias, people seek information that confirms what they already believe. And finally, one that is relevant for our field especially, called the gambler's fallacy. And this is the idea that if you flip a coin 5 times in a row and you get heads each time, the next time is more likely to be tails. It feels like that should be true, but it's not. The gambler's fallacy. So in Europe, where the thinking behind what I'm talking about began, what was going on before the 1600s? Okay, so this was like coming out of the Dark Ages. So doctors and scholars knew in like 1500 about what they did in 500 AD during the kind of the height of the Roman Empire in Europe. So doctors and scholars knew about what the ancients knew. In some cases, they knew less. The word scientist at this time did not exist, and the concept of science did not exist, certainly not the concept of science as a social enterprise. So again, not really more advanced than at the height of the Roman Empire. Politics at this time was a series of wars, revolutions, and rule that was often corrupt and oppressive. And in particular, this was the time of the European wars of religion. So this consumed much of the 1500s and 1600s in Europe. I couldn't find a better diagram of it, but you can get a sense of the span of these wars over time and the spread of these wars throughout Europe. So the different colors are different areas of Europe. So a lot of warfare spanning a good 200 plus years, many generations, 6 or 7 generations of constant warfare. And so these wars, as a historian is quoted, these were more than religious wars. Nominally, they were about religion, Catholics versus Protestants, and among Protestants, different elements of belief, but really they were also about power and political advantage. And so it was such a catastrophe. These wars lasted for generations. Large numbers of people were killed. If you want to look at really horrible images, you can search for European wars of religion and look at some of the woodcuts that were made at that time by people living through the wars. I mean, it was such a catastrophe, though, that it laid the foundation for new ways of thinking. New ways of thinking, what is the truth? How do we determine the truth? Do we have to go to war to achieve the truth? And a very important intellectual set of ideas to come out of this period of tumult and warfare and chaos were the 3 liberal social systems. So here, I'm not talking about the American version, the American political definition of the word liberal. I'm talking about the original definition of the word liberal. And the kind of the dictionary definition is willing to respect or accept behavior or opinions that differ from one's own. So during the wars of religion, people whose beliefs differed from yours, you tried to kill them and they tried to kill you. So liberal was like, let's find another way to do this. So the 3 liberal social systems were an economic ideas that led to the Industrial Revolution, political ideas that led first to the American Revolution, and then later the development of liberal democracy across much of Europe. And then the one that is of most interest in this talk, the epistemic system that led to the scientific revolutions. So here, epistemic, a word meaning relating to knowledge or the degree of its validation. How do we determine what is true? What is true knowledge? These are epistemic questions. So all of these are social revolutions. They're revolutions that groups of people got together and did. And they're all related and yet separate, and they're all traceable to philosophical breakthroughs, primarily in the 1600s and 1700s. And the people most responsible are these: Adam Smith, here, John Locke, and James Madison. Now, these are considered the big three of modern liberalism. And I just want to point out that all of the pictures of people I'm going to show in this talk are men, and they're all European men. These people were all, flawed with the inequalities and blind spots of their time. So they were all men, for example. Nevertheless, without the ideas that they proposed, and when they proposed them, we would all live in a very different world. So I'm going to start by talking just one slide about the Industrial Revolution. The ideas behind all three are similar. So the founding documents of the Industrial Revolution, 2 books by Adam Smith, The Wealth of Nations and The Theory of Moral Sentiments. So he proposed a theory of human cooperation. He looked around him and saw, for his generation and generations before him, just generations of warfare and conflict. And he was a Scottish philosopher, so Adam Smith was Scottish. So, but he said, in addition to conflict, it was obvious that humans were wired for conflict. He said humans can also be oriented towards cooperation. Humans have a natural empathy for the feeling of others, and humans want to be trusted and respected by other people. So he proposed social rules to encourage and exploit human cooperation. And these rules were applied to the development of what we consider to be modern markets, free markets. So a very important aspect of his social rules, he accepted and realized that humans are ambitious and humans are greedy. But the right social order can harness these traits to the benefit of society. So you can be ambitious and want to start a company. You can be greedy and want to become rich, but you spend parts of your money and, the standard of living of other people goes up as well. So the success of market economics proved the correctness of his ideas. And this is not to say that markets are perfect or without problems, but they were much more successful than the centuries of warfare that preceded them. So market economics, we have a social primate, humans wired for personal relationships and small related groups. And yet, this social primate can cooperate impersonally across unbounded networks of strangers without any central authority organizing markets and issuing commands. And consider for a moment the fantastic complexity of modern items that we use, like the iPhone, like the Prius. And you could replace those with an endless variety of other amazing examples. The technology. It's impossible for any one person to understand more than a tiny fraction of what's in either of these devices. Like other modern cars, a Prius has many, many, many different computing nodes in it, for example. Like I think more than 100, something like that. So the Industrial Revolution. The next, the American Revolution. And so the founding document here, the American Constitution. Now, James Madison is not the only author of the Constitution, But if the Constitution was a paper, he would be the lead author. He was the primary supplier of ideas, and he brought to the Constitutional Convention the deepest understanding of prior work in political philosophy. It's based on a theory of natural rights, that human beings have natural rights that accrue to them because they're humans, because we are humans. And it's another example of social organization, but without centralized control. The genius of the American system, which of course, it doesn't always feel like it's a genius system, doesn't feel like it is right now, certainly. And other nations have developed other ways of expressing representative democracy. But the central idea is pitting people against each other. As Madison said, ambition, that's the great danger of trying to set up a democracy. People will have the ambition to become the tyrant, to become the ruler. Ambition must be made to counteract ambition. So that was kind of his organizing principle, one of them. So power is horizontally distributed among branches of government, legislative, executive, judicial, and power is also vertically distributed between the states and the federal government. The result of this distribution of power is that it forces compromise. So even this week, there was this compromise on the borrowing limit in America. I mean, it's messy, it's ugly, but the point is it was a compromise. And that was the point of the social organization of the entire system. And so success for this system so far in America and many other liberal democracies, and of course, we've seen the tremendous wealth that liberal democracies have created over the past 250 years. No tyranny so far in most of these democracies has generated great wealth. And I guess I'll end this little part with a quote from Winston Churchill. He said at some point, "No one pretends that democracy is perfect or all wise. Indeed, it has been said that democracy is the worst form of government, except for all those other forms of government that have been tried from time to time." So wisdom from Winston Churchill. So now the liberal order that is of most interest for this talk and this gathering, the scientific revolution. So I've provided a neat division, 3 philosophers, 3 revolutions, but the truth, of course, is messier. Other people were involved, and all of these people provided ideas to each other. So one is Miguel de Montaigne. He was a French philosopher in the late 1500s. And this is right, he lived right in the middle of the European wars of religion, in an area where there were such wars happening. And his work is really quite despairing. So he determined that for an individual, true knowledge is impossible. And he knew his own convictions to be untrustworthy. He saw, like all of us see, that sometimes we believe something and then we discover we were wrong. And therefore, everyone else's convictions must also be untrustworthy. And he said, the power of reason is but the servant of confirmation bias. So he was one of the first to really propose and study and come to understand what we call confirmation bias. He said, we can have the illusion of knowledge, but we can never have the real thing. The social implications of his work are pretty bleak. He said people are doomed to eternal conflict over their beliefs. This is what he saw happening all around him for the entirety of his lifetime. No 2 people hear, see, or believe the same thing. And he was aware of the idea of Leviathan and so forth. But he said authorities are also people, and they cannot determine the truth either. So His demolition of knowledge appears to reflect a kind of a nihilistic despair, but it contains an important hint. And that hint is that truth is not an individual problem. Truth is a social problem. And it suggests that true knowledge is not what I know, it's not what you know, it's what we know together. So another point in the development of these thoughts comes from Francis Bacon. So Bacon was an English philosopher and a statesman living about 4 generations after Montaigne, but aware of the work of Montaigne. And he wrote his most well-known work, Novum Organum, and like New Ideas, sort of. And he adopted Montaigne's skepticism about the inability for a human to come up with the truth, to know the truth. He proposed that true knowledge is not what one believes, but what comes out of the scientific method. He is considered the father of the scientific method. He proposed that people perform experiments and make observations and use inductive reasoning. And the goal of these experiments is to eliminate wrong answers and point towards right answers. So he's not the first to ever have these ideas, but he was the first to systematically describe them in this way. And he also founded the first scientific professional organization. And it was, I can't remember the name of it. I didn't write it down, but it's like the Royal Society of Science or something like that. And so he is considered to be the father of empiricism. And what's very important was the social promise that his ideas developed. So he proposed a way to reconcile disagreements. Previously, scientists, which at the time were called natural philosophers, they tended to split into opposing factions over scientific conflicts. The factions would not come together in joint meetings. They would just kind of form these tribes and write bad things about each other, just like the warfare that was all around them. By sticking to verified facts, the scientific method enabled practitioners to feel like they were part of the same scientific community, even in the absence of a commonly accepted theory. So the social promise of his method is that it took these conflicts off the street and into the lab. Everyone could feel like it could help to separate the ideas and the theories of science from the people involved. This was a very critical part in the development of the scientific method. So now we come to John Locke. He's an English philosopher and physician known as the father of liberalism. His ideas were also very influential in the American Declaration of Independence. So he wrote an essay called Essay Concerning Human Understanding, 1689. And he determined true knowledge is not what it is not. It's not innate. It doesn't come from revelation. It does not come from general theories. True knowledge instead comes from facts and data, from investigating the world, and here's the most important part, from comparing notes with each other. So he is the first to fully articulate the social implications of empiricism. Claims to true knowledge must be tested by others, testable by others, and others must so test them. So true knowledge, it has to be testable by others, and it has to actually be tested. True knowledge is established through persuading others. When a group of people come to believe something, it's more likely to be true than if any one of them believes it. Another very important aspect is that untestable claims. So he was the first to propose the idea that a claim has to be testable. If it's untestable, and in his day and age, that mostly meant religious, an untestable claim cannot be known and therefore is a private matter and must be tolerated. So he proposed the social importance of intellectual diversity, which found expression in the idea of freedom of religion, separation of church and state in the American Revolution. So, you know, intellectual diversity. If people have claims that are untestable and different from ours, we don't go to war with them and kill them. We live with them and let that be a private matter. So the goals of empiricism to him were twofold: true knowledge, but also peace, an end to the wars of religion. So this leads to some general ideas. And one very important one is the idea that mistakes are what we kill. We don't kill each other. True knowledge does not require certainty. And in fact, true knowledge is somewhat incompatible with individual certainty. So this brings up the idea of skepticism versus fallibilism. So for the skeptic, this is like a term of art in philosophy. For a skeptic, the goal is to seek the truth, but true knowledge is impossible. So another idea central to the scientific method, for the fallibilist, so embracing fallibilism, the goal is not true knowledge, but to search for error. It's not possible to find true knowledge, but it is possible to find mistakes, errors. And so the idea is you can never achieve final confirmation of any possible piece of true knowledge, but you can achieve disconfirmation of the portions of that knowledge which turn out to not be true. So, for example, you could see some birds and you could come up with the knowledge that birds fly, that all birds fly. And this knowledge can exist for a time, but then one day you see a flightless bird, and now the mistake is corrected. And you say, well, many birds fly, but some birds don't. And so the mistake is killed, and the knowledge is closer to truth. So separating the idea from the person, that was a big part of this intellectual development. We don't die, we let our hypotheses die instead, and therefore scientists are free to make mistakes. And so there was this notion of evolutionary epistemology. So a new hypothesis is like a mutation. Most will die, but a few will succeed and become new knowledge. So these things can be put together in two great rules for scientific truth. And really this slide is the pinnacle of this talk. So the first is the fallibilist rule. No one gets final say. So no one gets final say. A statement can be claimed to be knowledge only if it can be debunked in principle and to the degree that it withstands attempts to debunk it. So you must assume your own fallibility. You must assume everyone else's fallibility. You must hunt for your own errors. You must hunt for others' errors, even when you are confident that you are right. The other great rule, the empirical rule, no one has personal authority. So a statement can be claimed to be knowledge only if the method for checking it gives the same result. So this is the idea of replication. The method gives the same result regardless of the checker's identity and regardless of who first proposed the statement. So there is a complete separation of person from truth of statement, and true statements will be true no matter who does the work, no matter who confirms it. So there are profound social implications for both of these rules. No personal authority says, well, let me start with no final say. No final say. Knowledge is always provisional as long as it withstands checking. No one can claim to have a fully settled debate. So maybe for a long time you thought that all the birds flew because you didn't have any flightless birds where you lived. But later that debate was, that knowledge was brought closer to the truth by seeing a flightless bird. No one can claim to have fully settled the debate. If someone makes that claim, no longer science. No one can shut down a scientific debate. If so, not science. The other rule, no personal authority. Any claim can be checked by anyone. If a full professor can check the claim, then so can an undergraduate researcher in their lab or in a different lab. People and groups are interchangeable. Now, that doesn't mean that these ideas are easy to check. Checking might be difficult, might be time consuming, but in principle, it's possible. I got a PhD. Many of the participants here have PhDs. It was difficult, but it's possible. Other people could also get PhDs and that kind of specialized training. What does not count as checking is claims to authority by some sort of personal or group privileged perspective. So you could say, well, I have a PhD level training in psychology. Only I can check this. Your PhD is in something else. You can't check it. That does not count as, that's appealing to some sort of personal authority and should increase the level of doubt that what is being discussed is true knowledge. So let me apply these thoughts for a little bit to papers, peer reviews, and citations. So now I'm pulling this into our community, the ISMAR community, the VR community. So peer review, we all write peer reviews, and we learn, I hope we learn, that you need to say something positive, and that's true, but the real goal is to point out flaws, and it's related to what we've been talking about. We can't fully know what parts of a paper are true, but we can see this flaw and that flaw. And somehow, as the paper passes through the social organization of peer review, it becomes better, it becomes closer to the truth. So by resolving errors, improving structure, paper moves closer to the truth. But in the end, even when the paper is published, the truth is still provisional. After the paper is published, then it goes through a period where it collects citations or not. Citations can be considered additional votes for the truth of a paper, unless the citation is presented in the context of pointing out a flaw in the paper. So true papers continue to gather citations. Yesterday, we recognized a paper that 10 years on has received a very large number of citations. So there must be a very good kernel of truth in that paper to have so many citations. The ultimate fate of untrue papers is that they are ignored. The authors are not fired. Bad things don't happen to the authors. If you wrote a bad paper and thought you could be fired, no one would write a paper. And this ignoring occurs naturally. It's not that people purposely decide to not cite a paper. People are too busy citing other papers instead. And so peer review and citations are both kind of ways of moving a paper closer to the truth and then assessing whether a paper that has been published is close to the truth or not. So papers are entries in this larger social network of knowledge, and it's the network itself that generates the knowledge. So thinking about these ideas has helped me see papers in this larger social context. And so there's a concept in the book of the social funnel. of scientific truth. So this funnel operates for science as a whole. And the idea is that many ideas go in, many hypotheses go in, many of them. And this funnel is very efficient at getting rid of the false ideas, at getting rid of the ideas that are not true. So we saw this happen in real time over the past year with COVID. There was something like no papers about COVID in January of 2020. And then less than a year later, there were more than 100,000 papers about COVID. Many ideas go in, few ideas come out. And by the time the ideas come out, they tend to be true. Only a few of them. So the way that the social funnel works is it can efficiently get rid of many of these ideas. So when we apply this to our own professional community, we can see that the different kinds of publications exist in different levels along this funnel. So poster abstracts might be close to the left-hand side of the funnel. So, you know, there's not that much peer review for a poster abstract. And then a workshop paper, it's a little further down the funnel, but it's not as far along as a full conference paper. And a journal paper would be even farther along. But even when a journal paper is published, it's still, the ideas are not through the funnel. Then, are the ideas cited? Are they replicated? So replication papers that show the same result, they might be further down the funnel. And so as ideas go through this funnel, the confidence in the idea increases, but at the expense of latency. So we know that poster abstracts, workshop papers, that tends to be work that is recent, that is current. And by the time a paper is published in the journal, maybe several years have gone by. By the time that work is replicated, many years have gone by. And we have things like the Significant Impact Award for a paper that was published 10 years ago. So that's kind of the intellectual high point of this talk. I'm going to give one more example from medical science of the effects of this funnel of truth. And this is something that all of us have lived through for the past year and a half, and the reason why we're not together in person right now. So let's consider the virus, smallpox. Now, the history of smallpox, which I looked up, spent several hours looking at and making this slide. How can you really turn it into 5 different milestones? It's hard, but the point is, it took about 1,000 years from when smallpox was first described to when it was declared eradicated in the world. Still the only human virus to have ever been eradicated from the world. Polio was first, epidemics were first described in the late 1800s in America. And about 86 years later, the last US case was noted. So 86 years, an order of magnitude faster than smallpox. Coronavirus, which we all lived through, the amazing result, less than 1 year after the virus first reported, effective vaccinations were available. So final thoughts, final slide. Science is social, performed by individuals, but science itself is social. Just like economics, just like representative democracy. Progress in our field is therefore social. And this community, the ISMAR community, it's our scientific professional social network. It not only makes our science and engineering fun, it's not only fun to go to these conferences, it makes it real. And it ultimately makes it the truth and leads to progress. So I see that as more reasons to celebrate ISMAR and each other. So I have a short bibliography, contact information, And that is the conclusion of this talk. I think I will stop the sharing.
Well, thank you. That was really interesting. I feel like we got a good history lesson in addition to a science lesson. So I really enjoyed that. And we don't have a, we don't have a ton of time for questions. And I think you kind of started to kind of answer this one, but I guess one would be, kind of taking all of that into account. What is the action item for us? Like, what is the application of this for our little PERCxR community, the ISMR community, the VR community? What do we do with it?
What I think it helps me do is take a broader viewpoint perspective of what it means to have a paper accepted and what it means to have a paper rejected. So I don't know that there's anything concrete we should do except to continue to focus on the social health of our community, because that's where the knowledge is going to come from. It's not any one of us alone. It's the interaction between us. So my advisor long ago gave me an image of working on research that I've often thought about since he told me. He said, research is like you're in the desert and you're digging in the sand and you're looking for gems. And you're digging here or you're digging over there. And you don't know if you're going to find a gem. Now, you can use your knowledge to dig in certain spots, but you don't know if you're going to find a gem or not. If you're lucky in your career, a few times you find a gem, a few times. And so his point was you have to kind of take this broader, longer term philosophical approach to your work. You're part of this long scientific tradition, building on the thoughts of others, but you can't control whether or not you're going to find a gem. You can try, but you can't control it. So to me, that's kind of the takeaway. I realize as I say that, if you're not tenured yet, if you're a student, you don't have a job yet, that may not be very comforting,
I do think there's some comfort though, because there's a lot of negativity around the peer review process and in particular reviewer two. But I also think one of the things I've reflected on in the last couple of years is just the fact that I do feel that where the questions that you get asked, it's not an indication. Usually, sometimes people are being rude, but usually people are trying to understand it better. And so I think there is that takeaway of it also being a more positive thing that's making your work better. And also, as you said, more true. So there's a positive
something
side.
else I'll respond to there, having been program chair a few times and all that. It's just very important that the tone of a review is much more important if the work is being rejected. If the work is being accepted and you're the author, who cares if the reviewers liked your work or not? Ha ha, I got in anyway, jerks, like that. But if it's rejected, then the wording is very important, because as a community, what we don't want to do is annoy someone who might be poised to become a productive member of the community. We don't want to annoy them to the point where they say, to heck with those people, they're a bunch of jerks, I'm taking my work somewhere else. That's what we want to avoid.
And I think we may have one more question. I was trying to see.
Time for a longer question. I'll hang around.
Well, how about this? For anybody that wants to hang around for a little bit, please do. And I'll just go ahead. Also, okay, sorry to interrupt myself. Bobby, I can't promote you, so I don't know if Etienne, if you could, or if the technical assistants could do it. But would somebody promote Bobby so he can ask his question? And while that is happening, I'll just take this quick minute to I really appreciate everyone that contributed to this workshop today. I've greatly enjoyed it. I hope that y'all have too. In particular, I just really appreciate the senior organizers. So Bobby, Joe, Kiyoshi, Rick, Ed, all of y'all. It wouldn't have been the same without your guidance, feedback, and reviews. I also really appreciate my co-chairs, Etienne and Nayara. So thank you so much for all that y'all have done to help make this happen. And to the panelists, because y'all provided a lot of really interesting insights and ideas, and similarly to all the speakers that presented your work. And then finally, just to the attendees, I'm glad that y'all were here, and I hope that you enjoyed it as much as I have. So we'll kind of close it out officially here, but then hang out for more questions, and hopefully we'll figure out a way to promote those that want to have kind of deeper conversations.
Well, Bobby seems to be
so I'm here.
now.
I'm here. Yeah. Okay,
right.
so I wanted to go back to comments that you made at the beginning of the talk about distance misperception and how, you know, distance, that's been replicated and everything. And that's probabilistic reasoning, right? I mean, we have a p-value associated with that. There's also one aspect of that that you didn't touch on, which is that's reasoning in aggregate too, right? We say that, you know, most people underestimate distances, but there's a lot of individual variation on that. It's like saying that everybody can fit into an airplane seat or something like that, right? So how do you think that those types of things impact the type of scientific truth that you're talking about? I mean, because it seems fundamentally different, you know, because citations can get refined and these things can be refined. So what does it mean for truth, as you've talked about it in this talk, when you're talking about probabilistic reasoning or reasoning in aggregate?
So I think it means that, you know, when this was first proposed, the complexity of truth often grows. So, oh, Bobby disappeared. Oh, okay. The complexity of truth, often that confused me. I guess because I was looking at his face and now he disappeared again. He became a name. And now his face is back. Anyway, the complexity of truth, you know, increases. So at first there was this kind of simplistic idea that people underestimate. Also, you know, hypothesis testing, that has to be a very narrow question, but the truth about the world is always larger and messier and more complex. So sort of like the example of the birds, you know, maybe you grew up somewhere where you don't have any flightless birds and you think, well, all birds fly. And then, but it's not that the notion that birds fly is untrue, it's just more complicated. So I think the way that perception operates in virtual environments is similar. It's more complicated. And so kind of that body of knowledge moves closer to the truth. But I stated that as an example of a phenomenon that's been widely replicated. And really in our field, there's not that many phenomena that have been so widely replicated. The fact that redirected walking can be done in ways that people don't even notice. That's another phenomenon now that has been widely replicated. And that's kind of a remarkable thing. I mean, I remember reading the first paper I saw about redirected walking and thinking, boy, that's weird. Surely that, you know, I mean, I didn't think that it was going to be possible to replicate it as widely as it seems to be. So that was kind of a counterintuitive thing for me, at least. So, yeah, Missy asked if all panelists could be promoted. We could also just all go into GatherTown, I guess. That was the point of it.
I think that's a great idea, and I forgot that that was an option. So maybe we can wrap it here and all move to GatherTown if you're able and interested.
Okay, I'm gonna log off and go to GatherTown and be there in like 1 minute.
All right, see y'all there.
All right, thank you, Missy, and everybody who organized this. It was great.
Great, glad to hear it. Thanks, y'all.
Bye-bye.